Hello and welcome back, everyone. Thanks for joining us for day 2 of the inaugural Value Chain series on nickel. That's been brought to you by MetSoc. Hope everyone enjoyed yesterday's session where we talked about some of the broader thematics that some of the big banks and institutions like to understand before they get involved or come into sectors. And us sitting here as retail investors, it's also nice to appreciate their thought process too. I think we also got out of it maybe some of the things that we should be thinking about before we invest into the sector. Day 2 is going to be, I think, truly fascinating. It's kind of getting into the weeds a bit, but some of the stuff that we need to understand if we're to be better investors. So we're going to be looking at, the geology, exploration and mining of nickel. We're looking at processing. We're looking at refining and recycling. Now, these are all important things for us to be aware of, at least. And some of the people on here have put together some fantastic presentations and hopefully are putting it across in a way that we can all understand the kind of so what component. So what do we do now that we know this? I, for one, have gone trotting back to my portfolio and applying some of that thinking that I've learnt from these recording these sessions. So enjoy the day. Say welcome back. Thank you for being here, and do join in on those Q&A sessions. And first up today, we are going to look at geology, exploration and mining of nickel. And we've got 3 big hitters here. We've got Peter Fenato of Valles. He's going to be talking to you about existing nickel supply and resources. And then we've got Johnna Muinonen of Waterton. I think you'll know her from Dumont, a very big sulfide project. And also we're going to learn a little bit about deep sea nodules. So mining underwater, deep sea, from Ian Lipton, who's a consultant to Deep Green, one of today's sponsors.
Hi, everyone. I'm Peter Fenato. I have a degree in mining engineering from the University of British Columbia, and I've spent 30 years working for Valles. Spent the first third of my career up in Thompson, Manitoba, in the nickel sulfide mines, underground mines up there. And then the next 10 years in Indonesia, working in the nickel laterite mines for PT Valles Indonesia. And then lately I've been working in the exploration group for Valles, working on pre-feasibility studies. So I'm going to talk a little bit, very high level, about geology, exploration and mining. We'll talk about some of the differences in the main ore types. Talk about some of the discoveries, some of the implications of mining, where nickel mining is done. I thought I'd start with this interesting quote from the Nickel Institute that, nickel is quite common on the Earth. It's the 5th most common element on Earth. But yet in the crust, the average concentration is only 80 parts per million. Most of the nickel on the Earth is tied up in the Earth's core, where we can't use it for resources. So the nickel deposits that we do have in the on the Earth that we can extract are generally formed from mantle plume magmas. These are, as you can see on this slide, that comes from a detailed geology presentation from Professor Lecce at Laurentian University. These mantle plumes are associated in all the tectonic settings associated with plate tectonics, but some of the largest are in the rift-related ones. But so generally in exploration, you need to look for these systems. The metals within these systems are, still fairly low grade, 200 parts per million, 0.2% nickel kind of range, and they're in solution with the magma. These magmas intrude into rocks that contain sulfur, then the metals react with the sulfur and form sulfide minerals. Pentlandite, chalcopyrite would be the nickel and copper common minerals. and then the amount of sulfur and how quickly it reacts controls the form of these nickel deposits. So if there's a lot of sulfur, the sulfide minerals coagulate into massive sulfide type deposits, which tend to be higher grade. Less sulfur taking longer can form disseminated type deposits. These deposits are lower grade, but also tend to be larger. So these sulfide minerals are much more dense than the silicate rocks that they're associated with in the magmas, and need to have, they form within the plumbing systems of these magmas, and this can be intrusive, so within the rocks forming below the ground, where these intrusions, these magmas extrude onto the surface of the earth as a lava. They can also form deposits, settling in kind of nooks and crannies within this. Yeah. So that's important from the perspective of, need to find these systems, and then kind of the needle in the haystack of where the sulfide minerals have concentrated within these systems and how they have concentrated. Secondary minerals are also quite important in the for sulfide deposits. In this research from Wood Mackenzie, you can see that more than 60% of sulfide mineral production it has a negative C1 cost, and this is due to significant quantities of byproduct metals such as copper, platinum group elements. Norilsk is quite notable in this group, which has a very high concentration benefit from byproduct minerals. So when looking at companies and their nickel production, it's quite important to understand the byproducts in these deposits. The byproducts are controlled by the chemistry of the original magma, generally as the amount of magnesium MgO in the magmas increase, the copper grades decrease, as well as platinum group elements. Sudbury is a notable exception. When I talked about, most deposits are formed from these magmas from deep in the earth. Sudbury was formed from a meteor impact, and that's what created the magma. From that point, the similar processes evolved to form the deposit. On this slide, on the right-hand side, you can see a graph that maps the some of the key deposits in terms of size of the deposits and the grades of the deposits. So the two monster deposits, which are Sudbury and Norilsk Camp, they have Sudbury's been mining for more than 100 years. Norilsk was developed in the 1930s, have been mining for generations, and will still have many generations to come. This is kind of followed by Thompson and Jinswan in the 1960s, where again they've been the most significant deposits, but have been around and known about for a long time. Then the next couple in that, as you move to the left, you've got Voisey's Bay, which was discovered in 1994. It's the next most significant discovery. Discoveries since these have tended to be smaller or lower grade. For high-grade sulfide mining, generally these are mined now underground. Voisey's Bay is a notable exception. It's been mined by open pit but is now going underground this year. When you're looking at these high-grade sulfides for underground, the shallower ramp access mines like the Nova Bollinger mine in Australia, which has been recently developed, they're cheaper and much quicker to construct and than the deep shaft access mines like what are mined in Sudbury. Generally, higher grades are deposits can often be smaller and more irregular and need to be mined by expensive and labor-intensive mining methods like cut and fill, where the cost can be in the hundreds of dollars per ton. As the deposits get bigger and more regular geometries, then open stoping type mining methods can be used, and these are kind of in the $50 to $100, $40 to $100 a ton type cost range. And then there's some lower grade deposits which are quite a bit larger, and this allows us to think about much lower cost mining methods like cave mining. Some examples of this were Selby in Sudbury, which was mined by sublevel caving in parts of the deposit, and the Leinster B11 deposit in Western Australia, which is now being mined as a block caving deposit. And block cavings, these caving costs are in the range of $5 to $25 a ton. So when you're looking at companies with high-grade sulfide deposits, it's important to understand not only the grades, but the geometries to understand what kind of mining methods can be used and how expensive those mining methods are. So nickel sulfide, high-grade nickel sulfides, it's as I said, like a needle in the haystack. The exploration methods, generally first have to find the haystack, and then using conventional exploration methods. But then it's down to drilling and downhole geophysics to look for the needles in the haystack. Since Voisey's Bay in 94, Nova Bollinger is sort of a notable discovery in 2012. And as I said, since then, it's been either lower grade or smaller. If you look at the bottom of the slide, this is some research from S&P Global Market Intelligence. And if we look 15 years ago, from 2006 to 2013, spending on exploration was in this $600 to $700 million a year range. And then after 2012, after Nova Bollinger, it's been about half that at 300 million. Should note that these numbers are based on both sulfide and laterite, but the numbers are dominated by sulfide exploration. So who's doing exploration? Looking at the top, you can see 69% is major companies. This is companies like Valles and Norilsk and BHP. And only 25% or so with smaller companies. Most of the money is being spent at the mine site. So either improving confidence in existing reserves or looking in and around existing mines, with only 20%, 21% grassroots exploration looking for that next haystack. And then finally on the bottom, you can see that between Australia and Canada, they see more than half of the exploration spending. So that's nickel sulfides. So moving on to nickel laterites. Nickel laterites form from the same ultramafic rocks. And if they intrude in tropical areas that have high rainfall with dense vegetation, and over millions and millions of years of rainfall. That rainfall becomes slightly acidic with the rotting vegetation from leaves and such, and that leaches away the MgO in those intrusion rocks. So those rocks originally started with 0.3% nickel, 35 to 45% MgO. As we look at the weathering that happens, that the weathering process is what upgrades the nickel from that 0.35 to grades that become mineable. So as we look at the fresh rock to the surface of the profile, those are the most weathered rocks, and that MgO content reduces down to virtually nothing. And so that removal of that material naturally upgrades the amount of nickel and iron that remain. In the top of the profile, where once the MgO is gone, then the nickel becomes soluble without the presence of MgO. That nickel gets dissolved into the water and then descends into the profile. And then once it hits the saprolite layer, the nickel precipitates out and more MgO is removed, and that process continues and continues, and that profile grows. So what we see is in the saprolite profile that's directly on top of the fresh rock, the nickel grades can range from 1.5 to 2 or even 3 or 4% nickel. And this is the area that's targeted by smelting processes. So the ferronickel, the nickel pig iron, or the nickel matte smelting like it's done at PT Valley. On top of the saprolite layer is a layer of limonite. This is an area targeted by leaching processes. So the HPALs, like at Goro, and in this area, the nickel grades range from about 0.8 to 1.5%. So in terms of the world resources of limonite, about 60% are in the limonite zones, and about 30 to 40% in the saprolite zones. So these generally form on hillsides where the drainage profile is good, so that this process can occur. So from an exploration perspective, these deposits are easy to detect because of the high iron. They've got unique vegetation. And so, yeah, we know where they are. They're all on surface. They're all mined by open pit, quite cheap to mine. There's no drilling or blasting required. However, the challenges around the limonite zone is very fine particles, and in the tropics, this is mud. So there's a lot of sand and gravel, rock and gravel required for road construction. It's quite a challenge. PT Valley spends a lot of effort to ensure that this limonite doesn't get into the rivers and streams and form sedimentation. And this high moisture content, both in the limonite and the saprolite, give material handling problems. It behaves like a slurry when it's being handled. It needs to be dried with solar drying before it can be put into ships. There's been several accidents with ships sinking due to too high a moisture content in the ore of ships in between Indonesia and China. For mining the saprolite, the profile is quite irregular and needs small equipment to mine the ore in the saprolite. And then these unique vegetation that forms on these laterite deposits need a considerable multi-year effort to rehabilitate them after mining. As mining of one area finishes, the overburden from the next mining area is placed, but it's a lot of work to get the original vegetation back the way it was. So where's nickel mined? So from this research from Wood Mackenzie this year, you can see that they're predicting 2.6 million tons of nickel production for 2021. Of that, 1.8 million from laterites and 700,000 from sulfides. The key sulfide producing countries are Russia, Australia, Canada, and China. And from the laterites, the key countries, Indonesia, Philippines, New Caledonia, Brazil, Australia, Guatemala, Cuba. In terms of world nickel resources from the USGS, they tabulate 94 million tons of reserves. So this is material that is either being, these are current mines or mines that have feasibility studies. Indonesia, Australia, Brazil cover about 60% of the world reserves. And at 94 million, it's 30 plus years of ore supply. Expanding that to look at resources, this is from the Nickel Institute. You see that in terms of sulfides, we're seeing about 118 million tons of resources of nickel, dominated South Africa and Russia, Canada, and Australia. In the laterites, a bit more at 178 million tons. Again, Australia, Indonesia, Philippines, New Caledonia, Cuba, some notable countries. So looking at the laterites and sulfides together, nearly about 300 million, so about triple the reserves. So it takes us close to about 100 years worth at today's type production rates. And then they estimate another 300 million or so in nodules, which Ian will talk about later. And then just a little bit of the history of where nickel production has gone. So if we look 15 years ago in 96, we see there was about 1 million tons a year being mined. That was about 60% from sulfides and 40% from laterites. And as we move today, it's the amount of sulfide production has stayed about the same, and all the growth has come from laterites. So that's my quick tour through conventional nickel geology, exploration, and mining. Thank you.
Hello, my name is Johnna Muinonen, and today I am going to be here talking to you a little bit about nickel ultramafic deposits as part of the value chain series on nickel. So, nickel ultramafic deposits, why are we talking about them? What are they? And you know, one of the things is, as nickel demand is forecasted to increase, as we see that sort of demand rise from the use of nickel in batteries, as we transition to a more sustainable energy future, additional sources of nickel are needed. There's some various different nickel sources around the world, laterites, sulfides, and one of the subsets of sulfides that I'll talk to today is nickel ultramafic deposits. Generally, these deposits are lower grade compared to typical sulfide deposits, but they have the ability and the scale to deliver significant annual nickel production. And many, one advantage of these is many of them are located in a tier 1 mining jurisdiction. So many are located in Australia and Canada. And that looks at, in terms of addressing geopolitical risk, and where we look at where nickel is coming from and where new nickel is coming from, ultramafic nickel deposits can play a role within that. If we look at the past 10 years of where nickel has come from, most new nickel, not all, but most new nickel has come from Indonesia, and that trend will continue. However, as large automakers and mining companies look around the world to add nickel into new production, they are going to start looking at some alternatives. One other piece, especially the ones in Canada, is when we look at ESG credentials and we look at greenhouse gas footprint, many of these large nickel ultramafic deposits are located near existing hydroelectric infrastructure. Which means, electricity is one of the biggest costs and mining is one of the biggest consumers of energy. And when we've got clean, green hydroelectric energy, it lowers our greenhouse gas footprint overall. And in addition to this, one of the interesting features about nickel ultramafic deposits is the minerals that are contained within the ore bodies can naturally and permanently sequester carbon dioxide. So not only can these deposits provide nickel for a green, sustainable energy future, they can also actively sequester carbon dioxide from the atmosphere. So what are some examples of these, and where are they mined now? Where could they be mined in the future? If we look at some of the current and historical production, we have seen some of these nickel ultramafics mined historically. Specifically, Mount Keith is probably the largest and the most well-known one, and it's been mined since the mid-90s in Australia. And recently, BHP has just put Yakabindi, which is another large-scale, low-grade nickel ultramafics into production late last year. We have Santa Rita in Brazil, which is a smaller one that's currently on care and maintenance, but depending on nickel prices, may come back into production soon. And then back in the 70s, there's a deposit that is owned by Valles called Pipe, and it was milled in the 70s through the Thompson Mill. There are quite a few development projects. This list is in no way meant to be all-inclusive. I just picked a few examples of ones that are sort of people know about that are out there. In Australia, there's Honeymoon Well. In Canada, there's projects like Crawford, Dumont. We've got ones out in BC like Turnagain and Baptiste. Nickel Shaw is up in the Yukon. And then there's Pipe, which was mined in the 70s, but has not been mined out and has a much larger ultramafic resource extending around it that's currently owned by Valles and not in production. And in Sweden, there's one called Ronbacken. So what are some of these characteristics of ultramafic deposits? What makes them different than existing nickel sulfide deposits today? Lower grade tends to be economic, you need a larger scale. And this larger scale is bigger than what we would traditionally see nickel sulfide deposits mined at. So when we look at these ultramafic projects, you're seeing things in sort of the 30,000, 50,000, even up to 100,000 tons per day, or versus a more traditional nickel sulfide plant that you would historically have built, which would sort of be 10,000 tons per day. So when we talk about Dumont and when we talk about sort of where these could fit a role, they're more comparable to, say, these large copper porphyries that we see down in South America, or things like Highland Valley Copper or ATIC up in Sweden, where we see lower grade, large scale mines. If we go into the ultramafic mineralization, so the difference between this and, say, the typical nickel sulfides is, sorry, I'm going to repeat that. Hopefully you can cut this part out. So let's talk about what the ultramafic mineralization. And I think one big piece of this is when we look at nickel and when we look at nickel deposits, is that one of the unique aspects about nickel that's not found so much in copper and other base metals is that nickel can occur in different minerals, and including minerals that cannot be upgraded economically. And so that's a big key when somebody's looking at a deposit. So it's not unique to ultramafics. Traditional nickel sulfides have nickel that's in pyrrhotite and pyrite iron sulfides, which is recoverable, but not completely recoverable at economic concentrate grades. But the nickel in ultramafics is not just contained within pyrrhotite and pyrite when they exist, but it's also contained in the actual rock or the silicates. And the lower grade nature of the large ultramafic deposits means that this presence of nickel in the silicates has more impact, can have more impact on the overall recovery of the deposit. And really, when you're looking at different nickel ultramafics and when you're looking at nickel ultramafic projects, you really want to understand where the nickel is and how much of it can be recovered and how does it vary through the ore body. Because that's really what's important to the economics of these projects is understanding that and seeing test work and data to support those recoveries and that understanding. In addition, nickel ultramafics, while most massive sulfide deposits are traditional nickel sulfide deposits, the primary nickel mineral that's recovered is called pentlandite. Nickel ultramafics have lots of pentlandite in them, but they can also have very commonly things like hazelwoodite or awarite. And these are actually have much more nickel within the mineral compared with pentlandite. And so that generates some really high grade concentrates, which gives you a lot of flexibility when you look at how you want to treat the concentrate downstream. So in terms of, does it go to a smelter or does it go directly into a roaster, into ferronickel, or even does it directly feed the battery industry? So there's lots of different options when you have a nice high grade clean concentrate. You know, the reason these are called ultramafic deposits is really the presence of high levels of magnesium rocks. And these magnesium silicates that are in the rock, in these ultramafics, can cause some thick slurry, which makes flotation difficult. So sometimes sometimes what they have to do is they have to remove these ultrafines to mitigate this issue. And then once these slimes are removed, not everybody does it, but most of the mills, so Mount Keith, Santa Rita, they all have a slimes removal circuit. Once these slimes are removed, the sulfides can then be recovered by very traditional processes. And to remove the slimes, we use a very traditional hydrocyclone, which we'll talk a little bit more about in the mineral processing side of things. So I think, from the, understanding these, looking at the opportunity, they are a bit different than traditional nickel deposits, but there's an opportunity when we look at what we want to do in the future and where new nickel is going to come from in the future to look at these deposits slightly differently than the way we've looked at other nickel deposits in the past. But really, the key to understanding is scale. They need to be big, and they need to make them economic. They generally need to be big, as well as understanding the nickel recovery. Because nickel, especially in ultramafic deposits, the nickel can be present in a variety of forms. We need to make sure that we understand, or that the projects we're looking at, we understand how that nickel is recovered and which portions of the ore body have recoverable nickel. So that's really important when you look at nickel ultramafics. But I think there's a huge opportunity for these to provide feed for the future when we look at where all this nickel is going to come from as we move forward with a clean, sustainable future. Thank you.
Welcome. Today I'm going to provide you with an introduction to the amazing story of deep sea polymetallic nodule deposits. We'll look at how they differ from terrestrial nickel deposits in terms of their geology, exploration, and potential production method. The story starts with the HMS Challenger, which set sail in December 1872 from England on a voyage to survey the depths of the oceans. Over the 128,000 kilometer journey circumnavigating the globe, 133 bottom dredges were carried out. On the 7th of March 1873, the dredge hauled up on its deck several peculiar black oval bodies which were composed of almost pure manganese oxide. We now know that these nodules also contain significant amounts of nickel, cobalt, copper, and rare earth elements. And we also know, 145 years later, that polymetallic nodules cover vast tracts of the deep ocean floor, as this map from the Scripps Institute shows. You'll notice the particularly dense occurrence of nodules on the left of the map in the tropical waters of the Northeast Pacific Ocean, an area known as the Clarion-Clipperton Zone, or the CCZ. I'm going to focus today on the CCZ because it's the most intensely explored and it's remarkable for its high grades and continuity. This is a bathymetric map of the CCZ colored by depth. The magenta and blue are the deepest parts and the orange areas are the shallowest parts. The CCZ is a vast tract of seafloor of the Pacific Ocean between the Hawaiian Islands and the west coast of Mexico. And it's defined by two major west-southwest trending fracture zones that cut through the Earth's crust, the Clipperton fracture zone to the south and the Clarion fracture zone to the north. The depth of the ocean in the CCZ ranges from about 4,200 meters to 5,000 meters, so it's seriously deep water. These are three photographs taken a few meters above the seafloor by an autonomous underwater vehicle. Each of the dark objects is a polymetallic nodule. The nodules are typically 10 millimeters to 100 millimeters in diameter, roughly round when viewed from above, but elliptical when viewed from side on. The vast majority of nodules occur on the seafloor or are partially covered by sediment. Buried nodules are relatively uncommon. The nodules are interpreted to have precipitated from seawater at or very close to the seawater sediment interface. They appear to have grown slowly, perhaps over a few million years, soaking up metals from the seawater. The CCZ appears to be something of a sweet spot in terms of supply of metals, water depth favorable for the precipitation of the metals, and benign conditions for their preservation. The area covered by nodule fields within the CCZ is huge. This map shows that the area covered is about 5,000 kilometers long by 2,000 kilometers wide. The International Seabed Authority has estimated inferred mineral resources of 30 billion tons of nodules, containing 70 million tons of cobalt, which is about 500 years of supply, 400 million tons of nickel, and 340 million tons of copper. This is a truly remarkable accumulation of metals. This map shows the seafloor colored by nodule abundance, with the higher abundance areas in darker shades. And you can appreciate the continuity. Let's look briefly at exploration methods. These are, of course, all remotely executed. First of all, we need to know what the seafloor looks like. Multi-beam echo sounder is used for mapping the bathymetry. A multi-beam sonar system is a device typically used by hydrographic surveyors to determine the depth of water and the nature of the seabed. Most modern systems work by transmitting a broad acoustic fan-shaped pulse from a specially designed transducer mounted on the hull of the ship. The speed of sound in water can be determined for the full water column profile, so the depth and position can be determined from the angle and the two-way travel time of the reflected signal. In addition to mapping the depth of the water, many multi-beam systems are also capable of recording what's known as acoustic backscatter, which is the amount of energy reflected from the seabed. This value is co-registered with the bathymetry data and is often used to study the characteristics of seabed composition. It can be used to interpret areas of polymetallic nodule coverage or areas of barren volcanic rocks. In order to estimate mineral resources, we need to collect samples for assaying, and we need to measure the abundance of nodules at individual locations. This is done by taking samples from the seafloor using a free-fall grab sampler or a box core sampler. The weight of the nodules collected divided by the area from which they were collected is the abundance of the nodules in kilograms per square meter. Autonomous underwater vehicles, or AUVs, are often also widely used. They're operated a few meters above the seafloor to collect detailed quantitative photographs of the nodules and to map the geological and topographic features that may influence the formation or preservation of nodules or impact the way that they can be recovered. We'll look at each of these methods in a little bit more detail. Much of the historical sampling of polymetallic nodules from the 1970s to the 1990s was carried out using free-fall grab samplers. This cartoon illustrates how they work. The sampler is released from a ship and descends slowly to the seafloor under its own weight plus the weight of the ballast it's carrying, hence the term freefall. When it lands on the seafloor, the spring-loaded net bags close under the sampler, scooping up nodules and sediment. The ballast containers are also opened, dropping the ballast to the seafloor. Now, with positive buoyancy, the sampler slowly ascends to the sea surface. It has a light and a radio beacon by which it can be located and retrieved. The big advantage of freefall grab samplers is that they can be deployed and retrieved independently without the need for winching, so several samplers can be efficiently deployed without delays. The disadvantage with them is that smaller nodules may be lost through the netting, and the biggest nodules may be too big to be caught in the net bags, and the recovery may only be partial. For mineral resource estimation, better quality samples are preferred to increase confidence in the results. The box core is currently the sampler of choice. A steel sample box, open at both top and bottom, is lowered on a winch to the seafloor. This can take several hours, so it's less efficient than using the freefall grab sampler. The box cuts into the soft sediment under its own weight. When in position, the steel spade arm is released, and it swings under the box core to lock it closed. The box core is then winched back to the ship. The complete cycle may take 4 or maybe 5 hours, and only after the box core has been retrieved can the next box core be deployed. The photograph on the left shows field activities around a newly retrieved box core, and the photo on the right shows the top shot of the nodules inside the box core. This illustrates one of the main advantages of using the box core. It collects relatively undisturbed samples from which nodule abundance can be confidently measured. As I mentioned, AUVs can also be used to obtain close-up photographs and video of the seafloor. Photographs have been used by commercial explorers since the 1970s to estimate polymetallic nodule abundance. A predictive relationship can be established through measurement of each nodule's long axis and its weight. This graph shows nodule weight plotted against nodule long axis length. By measuring the long axis digitally and using the calibrated relationship, the total weight of nodules within a calibrated area of seafloor can be estimated. This process is known as long axis estimation. The benefits of photos over physical sampling were quickly recognized and include, for example, that they're much quicker and cheaper to collect than with a conventional sampler, and a larger sample area can be measured than with a conventional small sampler. A key limitation of photo-based abundance estimation is that in some areas, light sediment cover is sufficient to mask many of the nodules, which prevents an accurate estimate. Nonetheless, where this is not a problem, LAE is a valuable low-cost supplement to box core data. The method will probably become the preferred method for short-term operations planning. Turning now to the grade of nodules. We've already seen how phenomenally extensive the polymetallic nodule deposits are. Another truly remarkable characteristic of the nodule deposits in the CCZ is the low variation in metals grades. To provide a comparison, here is a plot of nickel and cobalt grades within a fairly typical nickel laterite deposit. The samples come from an area of perhaps 20 square kilometers, and we can see a wide spread of grades of both elements. The plot on the right is a similarly scaled plot of nickel and cobalt grades from the Norrie D area in the CCZ, which covers an area of approximately 25,000 square kilometers. We can see that the range of grades is very low and the data points form a tight bullseye. The very low variance means that estimation of grades in this style of deposit is very low risk. Grade variation across the whole of the CCZ is illustrated by these maps produced by the International Seabed Authority using data collected by explorers since the 1970s. The low variability at the deposit scale is reflected by the continuity of the grades over thousands of kilometers across the CCZ. In other parts of the deep seas, polymetallic nodules also carry elevated grades of rare earth elements that are essential for many modern technologies. Now we've measured grades and abundances at locations on the seafloor, we can turn to resource estimation. For polymetallic nodule deposits, this is a relatively simple two-dimensional task carried out in plan view. The deep sea floor is not flat. As new oceanic crust is forced up as molten lava in the East Pacific Rise, the seafloor develops a pattern of parallel hills and valleys. This is the most common landform on the ocean floor and indeed on the Earth. Within the central CCZ, the hills are typically oriented parallel to each other and trend north-northwest. We can see these hills and valleys in the map of the topography of the seafloor in the Norrie D area, which is on the screen now. Definition of the topography is important because there are areas such as these seamounts shown in green and these volcanic areas shown in yellow, in which nodules may not have been preserved. Seafloor topography will also likely constrain commercial nodule production. For example, recovery of nodules from the steeper slopes along these ridges may not be practical. These areas need to be excluded from the mineral resource estimates. Having mapped the extent of the areas interpreted to have nodule coverage, we can now use the box core, freefall grab samples data, and possibly long axis estimation data to estimate nodule abundance, mineral resource tonnages, and mineral resource grades. This plan shows the sample data used for the latest mineral resource estimate for Norrie Area D. Simple spatial averaging techniques such as ordinary kriging are sufficient to model the spatial distribution. And at the end of the estimation process, we have a two-dimensional map of nodule abundance and grades from which the mineral resource above a selected abundance cutoff can easily be reported. There has as yet been no commercial production of deep sea polymetallic nodules, but there are a dozen private and government-sponsored research organizations actively investigating production scenarios. The term mining is really a misnomer for the production of polymetallic nodules. All the nodules of commercial interest are sitting on the seafloor, and there is no need to remove unmineralized waste rock to get at the nodules, so no drilling or blasting is required. The basic requirements are illustrated here. A collection machine, probably self-propelled, is required to pick up the nodules from the seafloor with minimal disturbance. Tracked and screw thread vehicles have been investigated by several teams. The nodules will be fed to a pumping system, which will lift them to a production support vessel. The production support vessel will transfer the nodules to bulk carriers that will transport the nodules to a land-based site for processing. Several small-scale trials of prototype collection machines and pumping systems or skip systems have been designed and tested. These systems are adaptations of existing terrestrial or shallow water technology. The technical risks are moderately high at the present time, since no full-scale systems have yet been built and operated, but developing systems to operate at great depths should not be an insurmountable challenge, because the oil and gas industry already operates at depths of several thousand meters. On the environmental side, a significant number of studies have been completed over the last 40 years, including ocean currents, phytoplankton, biodiversity, nutrient chemistry, suspended matter, sediment dispersion, ecosystem function, and recovery from past dredge tracks and impact experiments. These studies suggest that disturbance is not likely to extend beyond mining areas, and that within mining areas, long-term impacts will be small. Arguably, compared to the environmental challenges of many terrestrial mines, the environmental impacts associated with deep sea nodule mining may be very small. In summary, seafloor polymetallic nodules form a significant resource of the nickel, copper, cobalt, and manganese that will be vital to the transition to a global economy based on renewable energy. Polymetallic nodule deposits have remarkably low variability, which significantly reduces the resource risk. While there is as yet no commercial production, design and testing of production systems is well advanced. Importantly, studies to date indicate that commercial recovery of polymetallic nodules could potentially be achieved with less environmental disturbance than is caused by terrestrial mining. More work is undoubtedly required in all these areas to bring nodules projects to fruition, but the outlook is very exciting. Thank you.
Hello everyone. Hello Peter, hello Ian, hello Johnna.
Hi.
Hello.
Great presentations, packed full of information and some pretty big numbers in there. We've got a short Q&A, lots of questions sent through, so I'm going to rush straight into them if I may. We talked yesterday about the demand numbers. We talk about it on our weekly nickel show, that we need all the nickel we can get. However, is ESG part of the solution or part of the problem? I think, Peter, you talked about potential water issues. There's also issues around people want to protect forestry cover on the ground. So how do we move forward with ESG?
Yeah, look, I think, you know, the laterite mining, just the nature of the laterites, in the finds and, you know, and where they are in the forest means that it is challenging to mine responsibly, but it can be done. You know, and I think, you know, I'm pretty proud of the work that's being done in PT Valley on rehabilitation, on sediment control and things like that. You know, you know, I guess as margins can increase, you know, hopefully those lessons can be transferred to the smaller miners and all jurisdictions, and it can be done well. But you know, I think there needs to be that demand from the people that are buying you know, to track. You know, Steve talked about yesterday, track how that nickel is being mined and how responsibly it is being done, because it can be done well. In the sulfides, you know, we have the mines tend to be underground, which are now, you know, technology is moving to the place where we can easily electrify mining in an underground environment. It's more challenging in the open pits, but it's moving in that direction. And then, as Johnna mentioned, with the Ultramafics, the low grade deposits have lots of magnesium. Certain magnesium minerals react with the carbon dioxide in air and form carbonate minerals, and can be part of the carbon sequestration thing. So I think it's all there. I think, you know, we can mine nickel in an ESG friendly way. It's just, you know, making sure that everybody's doing it to the same standard.
Right, and just one more for you, Peter. Does the pressure from big funds, from small shareholders, from the OEMs and EV companies, does that make an impact in decision making in large companies like Valles, or is this driven internally?
I think for large companies like Valles, you know, what I see is the internal pressure to be responsible, but also, you know, that the big investors, the BlackRocks, you know, and their public letters and things like that make, you know, that drives that performance, you know, that those targets. But you know, I think it's been an internal goal for some time.
Okay. I won't push you too hard on that one, Johnna. We, as retail investors, family offices, we're looking at the market. We see lots of nickel juniors out there. You're obviously looking at Ultramafics today, and that's what you know. But we see lots of high-grade nickel projects too. How do we value these companies? You know, is it about grade? I mean, at what point can we get a sense of what the economics are going to look like?
I mean, I think, yeah, so you have to look at a couple different things. I mean, grade is great, no question about it, but you also have to have scale and in the right jurisdiction and access and, you know, all of those other things. Grade on its own, you know, 500,000 tons of nickel at 4% may never be a mine. You know, so you need 500,000 nickel ore, may never be a mine. So you need to look at that. You know, you can't just take it in isolation. And same with the lower grade ultramafic deposits. You know, we start talking about the scale, and you know, I always think they're much more analogous to the copper porphyries, as opposed to looking at some of the more traditional nickel sulfides, where you're looking at orders of magnitude in terms of operating costs of the scale of these larger ultramafics. So I think you know, it's not a simple answer. It's not, you can just go out, you know, if you know, an investor's looking at a project and then they say, oh, it's 1% nickel and they've got this many tons. Unfortunately, it's never that easy. There's a lot of context that you have to put around it. That includes where they are, what they're mining, how much more of it, you know, what's the exploration upside, and then what's going to be their operating costs, their capital cost, how much is it going to cost to access, can it get permitted, et cetera, et cetera. So, I mean, I think there's a lot of pieces that go into that, and unfortunately, it's not quite as simple. But I think that if investors start to look at those things and start to look at those and ask questions, they should be able to get more information about what potentially could be good or not so good.
There's a great chart in one of Peter's slides which talked about the falling away of dollars spent on exploration around the world. It also indicated that Canada, Australia, Brazil might be the places to go if you were. Is the scale component also part of the reason why the exploration dollars aren't there? Because these are big budgets and that might be off-putting to investors.
No, for sure. I mean, you know, anything that's got 1 billion tons in it is going to require a significant amount of drilling. No question about it. You know, you have to get your resource. You have to get your resource defined, and that is just drilling. At the end of the day, you know, there aren't a lot of shortcuts to that. You know, they can get a lot of information about deposits, and there's lots of, you know, nearby ones that are, you know, ones that you might be analogous to, but you got to drill it out. So there are a lot of costs to that, but I mean, small, high-grade deposits also have a lot of drilling, because generally they tend to be very variable. They tend to be many of them are pod-like. I mean, I'm not a geologist, so I don't want to pretend that I am, but many of them are very pod-like and require very, very closely spaced drilling to be able to upgrade that resource from inferred into a higher class of resource. So I do think that some of these large ones, definitely, you know, I think that's true, Matt.
But if you look at the scale of the
yeah,
sure, please do.
Sorry. Yeah.
Yeah, and I think it highlights the importance of for the investors to see the pre-feasibility study and read it and try to understand it, because it's all the components of it. It's the geology. It's how variable it is, how big it is, where it is, what the mining method's going to be. All of those factors all play a role in, you know, what are the recoveries. All of those things are really variable between these deposits, and so you know, yeah, you could have a small high grade deposit that is very good, or one that is not very good, just by, you know, simple things like recovery or mining methods that are applicable.
So Peter, why did you go for PFS as the example and not PEA? But how many projects which have PEAs actually get into production? Good PEAs. Yeah,
it's the level of detail, right? So a PEA has broad concepts. There's still not enough known about the deposit. There's things like that. So yeah, PEA is very useful. It needs to be taken into context, in that We're talking about inferred resources. We're talking about, maybe only a couple metallurgical test results. So we don't know about the variability of the ore. A lot of nickel deposits can have part of it that has very good recoveries and part that has very poor recoveries. And you don't understand that at that early PEA stage. So, the PEA needs to be sort of pointing some potential. Is it worth continuing to invest in exploration? And then the PFS, is it worth then doing all this drilling to do the feasibility study to then bring it into the mine? But,
right, so it's not specific to nickel, but I was just wondering if you went for PFS because it's specifically for nickel, but it sounds like you could apply that to a number of commodities too. John, one more for you, if I may, because I'm just conscious of time, and I do want to speak to Ian, is where is the next big discovery coming from? Have we any idea?
I don't. No, I don't. I don't know. I think the geologists might be better enough to answer that question. I think, though, the exciting thing we're seeing in the last sort of year or so are more people talking about exploration, right? So the one thing we do know is that if we don't spend money on exploration, we're never going to find the next big thing. So yeah. I think that the fact that we're seeing lots of press releases and focus on, especially even with the majors, right? Because you didn't hear about that. But now you're hearing majors talking about wanting to go and find nickel, wanting to go and start exploring again. And I think that's been missing for a really long time. And I think nickel specifically, I think other metals suffered from this as well. But, historically, the majors used to have all their own greenfields exploration departments. That sort of transition to majors relying on juniors to go and do the exploration for them. And then all of a sudden, all the money dried up for the juniors, and none of that happened sort of for that last sort of suite of years, let's say the last decade or more. And now I think you're seeing more majors and all the way down the line saying, we need to go out and we need to explore and we need to generate new targets and new projects. So, I don't know where it's going to be, but I do think that it's exciting that we're seeing people wanting to talk about that.
I bet Ian's got an answer for me. Ian, where's the next big discovery going to come from?
4.5 kilometers down in the Pacific Ocean.
You know what? I thought you might say that. So look, you did a great presentation and laid it all out for us. So the numbers are there for people to see. We are making these presentations available to everyone, so it's all good. So I want to kind of get to the heart of the matter here, which is around the technology. So the two bits of it. How do you get it up from 4.5 kilometers down? And have you got some sort of sense of the economics about processing? Because that's the next tough nut to crack.
So well, let me take a step back. Go to the resource. The resource is relatively simple. We have the massive advantage of low variability. That not only reduces resource risk, but it also means when you come to process the material, that you have material which has low variability, and that's inherently easier than dealing with material that varies on a day-to-day or hour-by-hour basis. So that's a big plus. Obviously, you have to pick the nodules up, vacuum system, that sort of thing, and then essentially it's a pumping exercise to pump to the sea's surface, and from there. So I guess the biggest unknown is the actual operation of seafloor systems. This is it's going to push existing technologies beyond the depths that these things have been used before at a bigger scale than have been used before. But I think from the processing side, the routes that have been proposed are either pyrometallurgical with a hydromet back end, and the pyrometallurgical technology is pretty well established through a lot of the nickel laterite operations. So that's not quite such a stretch.
Okay, so you're saying that if you can get it up from the seabed, there's a process, you're not reinventing the wheel, you can extract economically, because they're very high grade numbers that you were talking about there. So again, we've got 1 minute to go, so I do apologize. There is an emotional component to this. We know there's a need, we know you've got volume, but the emotional component to this is maybe going to delay things. So what do you guys need to convey and get over to people to get over that hump?
Emotional with respect to what, ESG? Is that what you're thinking?
ESG, people don't like the thought of disturbing sea floor, seabed, any living any creature which may be down there. You're going to get a lot of pushback, I suspect.
Yeah, and that's a natural thing. But I think it is one of the attractions of these projects is that there is no waste to remove to get at the valuable materials. The impacts, a lot of studies show to date, are really quite small. Because the nodules are virtually pure metal, the amount of waste products that will then be produced on land-based processing facilities is also going to be very small. And the deposits are located in areas that don't have human habitation, don't really have any human activities other than a bit of shipping. Having said that, there is still a lot of environmental science to be carried out, and there's a lot of organisations working collaboratively to do that. And I think it's a case of educating not only the market and investors, but educating communities on a much broader scale as to the situation there and the manageability of risk.
Ian, thank you very much. I'm going to apologise to all of you because we only allow 15 minutes. Each of you deserves an hour. Fascinating topics in their own right. I would say to people, please send your questions and continue to send your questions in at the Q&A. Jeff and Boyd are answering where they can. Where they can't, they will get the answers and we will send those to you after the event along with the other materials. So Peter, Johnna, Ian, thank you so much for today. Really fascinating.
Thanks very much.
Thank you for having us.
Bye now. In this section, we'll be talking about the primary processing of nickel. We have three great speakers in this section. Johnna Muinonen will be presenting the mineral processing, the milling or the concentrating. Schonewille will be talking about smelting technologies in the primary processing. And Lourdes Valles will be talking about HPAL, which is applicable to the laterites. Primary processing of nickel is important because the primary processing is in the middle to make that intermediate for further refining. Because primary processing is the highest of volumes, this is where much of the capital and operating cost is.
Hi, my name is Johnna Muinonen, and I'm going to talk about mineral processing, specifically as it relates to nickel. Talk about some of the technical details, the stages that it goes through, and how to go from ore on the ground that's being mined into concentrate, which is really where the mineral processing field sort of stops and starts. I guess in terms of, I'll just do a quick about my background. I've been in the nickel industry now for roughly over 20 years. I spent most of my early career working at Valles in operations in Thompson, Manitoba, and then went from there and joined Royal Nickel back in 2010 to work on the Dumont project. Today I'm President Dumont Nickel, working to advance the Dumont project to a construction decision. So let's start off with what mineral processing is and maybe a little bit about what it isn't. So really it's around treatment of the ore, so the rock. So the miners mine the rock and the mineral processors take the rock and we separate and recover the valuable pieces from the waste or the gangue. And one thing I'm going to clear is we're talking about minerals. So we are recovering minerals. We talk a lot about metals, so nickel, copper, cobalt, gold. But really, when we talk about mineral processing and about what we're trying to get out, we're talking about the minerals. So each one of those metals exists as a mineral. Most of what we're talking today relates to sulfide minerals, so nickel sulfides, and how to recover those. But definitely, make sure, as you think about understanding what a mill does, is that we are recovering the mineral, not just a metal. There's more steps after that will take our minerals and turn them into metals, which I believe are going to be talked about by other people. So, it's the first process. So after the mine, this is the first process that takes the ore, and it's the first thing, and we are the first step in the process to go from a mine to finished metal. Most of the primary operations, the two big ones really are comminution, which is grinding, i.e. making something big and making it smaller. And then concentration or separation, which is taking the mineral you want and separating it from the minerals that you don't want. But there's also some other things as well as, dewatering, sampling, analysis also plays a huge role in the flow sheets of a mill. There's some alternative terms. So sometimes when you're reading through things, you'll come across mineral processing. Sometimes it's called ore dressing. That's very historical. Some older texts might refer to it as ore dressing. Sometimes it's just lumped in metallurgy. Metallurgy is a wide field that covers a variety of different disciplines, and mineral processing is a subset of that, as well as beneficiation. Another not as quite as common term, but you will see some of that. I am talking specifically on nickel mineral processing, and specifically we're talking about nickel sulfide mineral processing. Laterites, which are an oxide form of ore, very rarely undergo any processing or upgrading before they go into a downstream process. So really, when you're talking about mineral processing, you're almost exclusively talking about nickel sulfides. So where in the process do we fit? You hear people talk about metallurgy. As I said, metallurgy is a very wide process that goes all the way from anything that starts sort of after the mine, all the way to the metal, and then all the way beyond that as well once you get into sort of physical metals. But mineral processing is a subset, and really it's what happens in a plant called the mill or the concentrator. You'll see it referred to either one interchangeably, and they both mean essentially the same thing. And really it deals around size reduction, classification. So once you get a big rock to a smaller piece of rock, somehow you have to understand, we have to take that small piece of rock and separate it from the larger pieces of rock. Then separation, you need to take the valuable mineral and recover it. And then we produce products. Generally, the products are concentrate, and there might be more than one concentrate that comes from a mill. You could have a nickel concentrate and a copper concentrate, or you could just have a nickel concentrate, if we're specifically speaking about nickel, and tailings. So once you get the valuable mineral out, there's waste that needs to be disposed of safely, and that we'll call tailings. So I've sort of circled it here, and sort of we end when a mineral processing job ends when we make the concentrate, and then the concentrate goes downstream for further processing. So let's talk a little about size reduction. This is really the first step. It can also be called comminution. So you may see it called different things. Some people will, you'll see it called different things. Some people just refer to it as crushing or grinding. However, all of those steps really just talk about size reduction. And the goal is not just to get a smaller size. The real goal is to liberate or free up the valuable minerals from the waste. And that's really the goal. And generally to do that, you have to reduce the size. Typically, size reduction is made up of several stages. It's not just one stage. It's multiple stages as you go down. And basically, as you go through the stages, the material gets finer and finer and finer until you have enough, it's fine enough that you've liberated the valuable mineral from the waste. And so I put a couple of sort of just very, very general assumptions to give you a feel for what sizes I'm talking about. Crushing is generally the first stage. Sometimes that happens actually in the mine. Sometimes it happens in the mill. Sometimes it happens both. But really what that does is it takes the run-of-mine ore and reduces it to, say, sort of the size of a tennis ball. It might be the size of, sort of 6 inches. And then it could also be a little bit smaller. Some crushers make it smaller, but roughly it's taking it from like a really big chunk that comes from the mine to something that's about the size of your hand, your fist. And then grinding, which is the next step, then takes that sort of fist-sized lump and turns it into sand. And so crushing is generally done dry. So basically the ore comes out of the mine and it goes into the crushing plant or the crushers, and you don't usually add a lot of water or any water at all. But once you go into grinding, where you're trying to go from like a fist-sized lump to sand size, generally most mills add water. There's some exceptions, of course, but most mills add water, and you grind what's called a slurry. So when you take the ore and you mix it with water, you form a slurry, and you grind that. And typically when you're looking at a mill, grinding, crushing, comminution, size reduction, whatever they want to call it, is the largest energy consumer in the mill. So most of the energy in a mill is consumed in making the ore, taking it from something that's really, really big to something that's really, really small, so you can separate out the valuable minerals. Of course, once you grind them down, the next stage is classifying them. So you need to be able to say, this size is too big, it needs to go back. This size is the right size, it needs to move forward. because you don't want things going back and back and back, because that'll even cost you more energy. So once they're the right size, you want it to move through to the next stage. So there's a couple of different ways of doing this. Typically in a nickel sulfide mill, you would be, after grinding, you would be dealing with cyclones, which is the picture on the top there, right here, which is you pump the slurry into the top of a cyclone, and essentially it's exactly what it sounds like. It spins it around. The heavier stuff, or the bigger particles, come out the bottom, and the lighter stuff comes out the side. And then that goes on to the next stage. The stuff that comes out of the bottom, which is too big, goes back to grinding again. In crushing, where you've got bigger dry material, you probably have some screens that then say, okay, the screens, think about it, you're passing it just like a sieve that you have in your kitchen. You pass some dirt, you pass the rocks over it. The stuff that's fine passes through. The stuff that's too big stays on top and gets moved around again and gets crushed again. So there's a lot of work being done to separate out material that's already the right size, because you don't want to overgrind things. You don't want to send things back. It can cost you energy, first of all, which is very expensive, as well as you can actually make it too fine and make it difficult. So you want it, once it's the right size, you really want to move it along. And there's two main ways that you do that. One is cycloning and one is screening. In terms of things you want to see here is, in terms of when you're looking at studies and when you're looking at information, you really want to see some test work. Because one of the things you want to understand is energy, how hard is it? So how hard is the rock physically going to take? How much energy is it going to take to get it from big to small? Because that's very important. And rock comes in all a variety. Some is so hard it'll spark, and some is very, very soft and just kind of falls apart. So you really need to look and see, is there data that shows how hard it is? Is it hard, or is it relatively soft? So there's various different test work that you'll see as to design mills to understand, is it hard or is it soft? Well, once you've got it to the right size, then it's about separation. So in a nickel sulfide mill, the primary method of separation is called froth flotation. And essentially, you take the slurry, and it's a physical method of separation. So we're not changing the form, we're not dissolving it, we're not doing anything else. We're just taking that mineral that you've liberated from grinding, and you're attaching it to a bubble. There's a very small amount of chemicals added. It takes that nickel sulfide particle or copper sulfide particle, and it attaches to a bubble in a slurry, and it literally rises up, and the froth comes over the top. The froth that is produced is called the concentrate, and the slurry that comes out of the bottom of the cell is called the tailings. Now this shows one unit, which is one flotation tank. In a mill, there would be many, many stages of flotation, because one unit can't do everything. So to maximize the recovery, by recovery, I mean how much valuable nickel you're going to get, and the concentrate grade, which is the amount of nickel in the concentrate, to maximize that, you'll have multiple stages. So it's not just one unit, it's sort of, it could be up to some of the older mills would have several hundred units. The units can range in size between 2 foot cubed up to, the newest tank cells are sort of 600 meters cubed. So, I mean, it's a huge size difference as well. And it depends on how much, what kind of throughput the mill is processing, and how new the mill is. So what are some challenges that are specific to nickel? When we look at nickel projects, when we look at nickel mills, what are some of the things that are specific to nickel that are different from other metals potentially? And nickel ores, I think one of the few ones is one of the few sort of ore sources when you look at copper or other base metals, zinc, it is one of the few ores where nickel can occur in different minerals. So in nickel, you have the ore, it contains a variety of different minerals. Some of them contain nickel, but it's not just in one mineral. So it can be more complicated in terms of understanding where the nickel is and how to recover it. And so an example could be many nickel sulfide operations have the presence of iron sulfide. That iron sulfide can actually have nickel within it. Some, such as the Ultramafic nickel deposits, they can have serpentine or olivine, and those are silicate minerals, but they can also have nickel present in it. So it's really understanding, you do have to understand that nickel isn't always just in one mineral. Sometimes it's in a variety of minerals, And in many cases, it's not always economic to recover some of these minerals that contain nickel into the concentrate because it doesn't add value. So they have to be rejected to tails, and that can impact overall nickel recovery. And sometimes, however, we specifically look at nickel, sort of more traditional nickel sulfide deposits that have a significant portion of iron sulfides, which are called pyrrhotite or pyrite. Traditionally, a lot of those materials would be recovered to the concentrate, and it would increase the nickel recovery overall. However, it would lower the concentrate grades. So when we look at some of the historical and sort of the typical nickel concentrate grades, they tend to be a bit lower than, say, concentrate grades in the copper industry. So very much a traditional nickel mill would deliver something in the 12 to say 14 or 16% nickel in concentrate. And that compares to say over 25% copper and copper concentrate from a copper mill. And that is solely because we have this nickel that's present in other minerals that adds to the overall nickel recovery, and it's economic to recover them to some point, but at some point we have to stop. So I put a grade recovery curve off the side just to illustrate that, if you took 100% of the ore and moved it to concentrate, you would have 100% recovery, but you wouldn't have any upgrading. So you'd have to smelt or leach all of the ore, and that's not economic. So you have to start rejecting it. So the first thing you want to reject is the waste that doesn't have any nickel in it. And then there's a decision point about how much more waste you reject, but some of that waste will start to have nickel in it. And that could be from iron sulfides, or it could be in serpentine or olivine or magnetite. And so, you have to start rejecting that. So there's definitely a point, and it's this grade recovery curve where nickel concentrators balance that in terms of maximized recovery at a certain concentrate grade. But typically when you look at nickel concentrates, they will be generally lower concentrate grade than comparables in the copper industry. And that's really around the fact that the nickel can occur in multiple different minerals. Some challenges around nickel processing is around sometimes the silicate minerals, the waste minerals that are in the ore, can actually cause the slurry to be very thick. And you have to do some things to fix that and to make it amenable to a typical flotation process. Generally, a lot of places do that by adding more cyclones. So we talked about cyclones and size separation. We would add more cyclones and take that very, very, very fine portion that causes that thickness, which we call the slimes, and we could remove those and send them to tails. And then once you do that, the remainder of the flotation is very standard. So there are some specific challenges related to nickel that aren't seen in some other base metal mills. So finally, what are we producing? A typical plant or concentrator or mill will produce two products or three. One is called concentrate, and that's where the valuable minerals go. And this could be either one, depending on the ore, or two, and flow sheet. Sometimes some mills produce a nickel concentrate and a copper concentrate. Some mills just produce a nickel concentrate that can contain copper and then is later separated in further stages downstream. And then that concentrate is typically, for most nickel sulfide mills, is fed to a nickel smelter. That is changing as we sort of move forward with, if we look at sort of where the nickel market's heading. I think, we're going to see more and more nickel concentrates going to, either to a hydro processing for batteries potentially, or into, say, roasting and going directly into ferronickel for stainless steel. There's lots of opportunities there, but traditionally, the nickel concentrate that was produced from a mill would then go to a smelter. And that's really no different than, say, copper or zinc. And of course, we have the tailings. Now, the biggest portion of the ore that comes in generally goes out as tails. And this is the unvaluable product or the waste that's left over after removing the valuable mineral. And then this requires safe disposal. There's several different forms of disposal, and sort of you can use, depending on what your ore is, depending on where you are in the world, depending on your climate, and what geography you have around near you, there's a variety of different methods of disposal. If you have a lot of sulfur in your tails, underwater disposal is typically preferred to minimize acid mine drainage. However, you can do on-surface disposal, which is really creating a tailings dam to store them in. And then recently there's been a push towards looking at dry stacking as well, which is taking the tails and removing the water and being able to stack them directly on land. The water itself that is generated from this generally goes back to the mill for reuse. Water is a valuable commodity and is a precious asset to many mills, and so it gets recirculated back and starts again. So we try where we can to bring that back again to the mill. So I think that what I wanted to do today was give a very brief overview into the sort of the stages of mineral processing, specifically as it relates to nickel sulfides. Going through the mill, going from size reduction into size separation, into size classification, into separation, and then onwards with the products that we get from the mill and how we either send them to market through a smelter or dispose of them for tailings. Thank you.
Hello, my name is Ron Schonewille, and I'm the manager of metallurgy at Glencore Nickel, based in Toronto. It's my pleasure to speak to you today as part of the MetSoc Value Chain series. I'll be reviewing some of the key aspects of primary nickel processing. Historically, primary processing of nickel has been dominated by smelting. However, I will also point out where leaching processes are slowly making inroads into the nickel industry. My aim is to provide you with an understanding of the current state of nickel processing and where I think the industry is headed. As you are likely aware, there are two general types of nickel ore deposits, sulfides and laterites. The key differences between these two ore types start with the nickel-bearing minerals. Unlike sulfides that contain sulfur, laterites are composed of hydrated oxides. As a result of the mineral composition and grain size, nickel sulfide ore can be pre-concentrated by a factor of 5 to 10 prior to smelting. This is economically important since the cost of pre-concentration is much lower than smelting. Laterite ores are generally not amenable to any significant degree of pre-concentration due to the physical and chemical nature of the minerals. Nickel sulfide deposits are commonly associated with a variety of additional pay metals. For example, in PGM deposits in South Africa, platinum and palladium are actually the primary metals, and nickel is considered the byproduct. In nickel laterite deposits, cobalt is the only other pay metal. However, since it is not easily separable during smelting, it is actually considered an impurity in the final product. The job of the smelter is to enrich the nickel content by eliminating impurities. In addition to the sulfur contained in sulfide ore, both ore types contain iron and inert rock known as gangue. There are two general processing routes for smelting nickel sulfides: roaster electric furnace smelting and flash furnace smelting. Variations of these two flow sheets have been adopted to increase efficiency and improve environmental performance, such as the Dawn process. Laterite smelting is dominated by a single process, rotary kiln electric furnace smelting. Laterite smelting requires a higher operating temperature due to the composition of the gangue minerals, namely the high concentration of magnesium oxide. Due to the high process temperature in both processes, smelting is energy intensive. The primary energy sources for sulfide smelting are the sulfur contained in the concentrate itself and electricity. Owing to the absence of any fuel value in laterite ores, fossil fuel is required for the process. The product of nickel sulfide smelting is low iron nickel sulfide matte. The matte undergoes refining, where the remaining iron and sulfur are removed and byproducts are recovered. High purity class 1 nickel cathode is the typical end product. The product of nickel laterite smelting is class 2 ferronickel, containing typically 20 to 40% nickel with iron as mostly the balance, which is sold directly to stainless steel producers. The iron is desired by the customer since it's required in stainless steel production, thereby displacing alternate purchase sources of iron. In addition, iron contained in ferronickel has low impurities, unlike scrap steel. However, the customer generally doesn't pay for the iron units in ferronickel, and the producer typically pays for transportation to the customer. Furthermore, reducing the nickel content of the product increases the smelting costs. Therefore, a lower grade nickel product benefits the customer over the producer. Sulfide smelters have been progressively reducing sulfur dioxide emissions over many decades as their role in the detrimental effects of acid rain became clear. Laterite smelters have a significant CO2 footprint that will need to be addressed in the future as part of global climate change initiatives. This slide illustrates the two main processing routes for smelting nickel sulfide concentrate. Nickel sulfide concentrate typically contains copper, but the nickel to copper ratio really doesn't affect the process. In the roaster electric furnace process, concentrate is roasted in a fluidized bed roaster to remove a portion of the sulfur and oxidize a portion of the iron. All of the energy comes from the concentrate itself, so no additional fuel is needed. We call this an autogenous process. In the electric furnace, the roaster product is melted using electrical energy. After melting, the gangue and iron oxide form a slag layer that floats on top of the remaining sulfide matte. The slag is skimmed from the furnace and sent to disposal. The sulfide matte, containing about 50% nickel plus copper, is processed in a converting furnace. In this furnace, air is injected into the molten matte to further oxidize iron and sulfur. Converting is also autogenous. The final matte typically contains about 78% nickel plus copper plus other byproducts, up to 2% iron, and around 20% sulfur. In the flash furnace process, the reactions taking place in the roaster and electric furnace are combined in a single furnace. To meet the energy requirements of the furnace, bulk oxygen is required. A small amount of fossil fuel is also typically needed. The product matte and slag are similar to that generated in the electric furnace and are treated in a similar manner. In both flow sheets, the converting furnace slag contains a high concentration of nickel and is treated either in the primary smelting furnace or in a dedicated electric furnace to recover that nickel. The roaster, electric furnace, and converting furnaces produce a significant quantity of sulfur dioxide that is typically converted to sulfuric acid in an acid plant, which is a saleable product. The main differentiators between these two processes are electrical energy consumption and metal recovery, and they trade each other off. Energy consumption in flash smelting represents the energy required to produce the bulk oxygen, which is not insignificant. Although cobalt is not present typically in high concentrations, historically the price of cobalt has been up to 10 times the nickel price, so it's an important economic factor of the process. The process used for smelting nickel laterite ore bears some similarities to the electric furnace process for sulfides. Due to the absence of sulfur in the ore, fossil fuel is required for drying and preheating the ore. In the rotary kiln, approximately half of the nickel is reduced from oxide to metal using carbon. In the electric furnace, the remaining nickel and a portion of the iron are reduced to metal. Control of the extent of iron reduction determines the nickel grade of the product. The crude ferronickel tapped from the furnace is refined directly in the tapping ladle to remove impurities such as sulfur and phosphorus, yielding a saleable product. The slag tapped from the furnace has a low nickel content and is sent to disposal. Both laterite slag and sulfide slag are considered to be inert and are commonly used as a construction material. Due to the lack of concentration, electrical energy consumption is significantly higher than that for sulfide smelting. The nickel sulfide smelting industry is characterized by a small number of processing plants that were designed specifically for the associated ore body. Many of these smelters have exhausted their maiden deposit and have adapted to treat either new ore bodies or purchased concentrates. Each smelter is typically tied to a purpose-built refinery designed specifically for the characteristics of the smelter matte. As a result, nickel concentrate and matte do not have a broad commodity-type market, such as that found in the copper industry. The nickel sulfide industry is presently constrained by the lack of new high-quality ore deposits. Conversely, there are a large number of operating and undeveloped nickel laterite deposits. Although nickel is the 23rd most abundant element in the Earth's crust, below titanium, strontium, and vanadium, there have been a large number of nickel laterite ore body discoveries. Indonesia, the Philippines, and New Caledonia hold significant laterite ore reserves and have been an important part of the growth in nickel production over the past 15 years by supplying nickel laterite ore to Asia. The nickel laterite industry is characterized by few differences between operations as a result of the similarities between ore bodies around the world. The main differentiator is the product grade, which varies based on the iron to nickel ratio in the ore and the end customer. Tsingshan and other nickel laterite processors from China have been responsible for the emergence and rapid growth of nickel pig iron in China and subsequently Indonesia. They have changed the business model established by the nickel laterite industry by integrating downstream into stainless steel production. At the same time, they have placed less emphasis on owning the mines required to feed their smelters. Nickel pig iron, or NPI as it's known, is not really a new product. It's ferronickel with a lower nickel and higher iron content. The lower nickel grade stems from higher iron recovery in the smelting furnace, typically around 90% in an NPI operation compared with less than 50% in a conventional laterite smelter producing ferronickel. Global production of NPI has grown to supply nearly 50% of the nickel market in less than 15 years. It's been phenomenal. First generation NPI plants were based on adapting idle iron-making blast furnaces or idle ferroalloy electric furnaces. These plants were very inefficient, very polluting, and they no longer operate. Second generation plants were purpose-built for NPI production, but typically included minimal pre-processing of the ore ahead of the electric furnace. The current generation of NPI plants are pretty much indistinguishable from ferronickel plants. They use the same equipment, deliver comparable energy efficiency and nickel recovery, and achieve comparable environmental performance. This might not be something the established nickel industry wants to hear, but these observations are based on firsthand knowledge from visits to a number of these plants. The differences in NPI production lie mainly in the business model. Equipment is highly standardized with no custom design. Rather than aiming to maximize economy of scale in a single line, the equipment is of very modest size and typically operated below its rated capacity for ease of operation. Typical nickel production from an NPI furnace is about 25% of that in a modern ferronickel plant. All these things contribute to construction in less than 1 year, ramp up in 2 to 3 months, and high operating online time. Economy of scale is achieved by operating a large number of parallel lines. The Tsingshan Morowali operation in Indonesia presently operates 40 parallel RKEF lines with an additional 10 lines in construction or planned to be in operation by the end of 2022. And this is in addition to the production of ferrochrome, ferrosilicon, stainless steel, coke, carbon steel, hot rolling, cold rolling, and power generation all on the same site. It's extremely impressive. To understand where the primary nickel processing industry is headed, we need to look at the current pathways from ore to market. Currently, production of nickel is derived 70% from laterite ore and 30% from sulfide ore. This is the result of a significant recent trend towards laterite processing. For both ore types, smelting is the dominant processing route. The majority of laterite ore smelting operations produce NPI or ferronickel. But there is one important operation that produces matte for refining to class 1 nickel. I'll talk about that in a bit. Laterite leaching and all of sulfide processing operations also produce class 1 nickel. Nickel pig iron and ferronickel can only be utilized for the production of stainless steel, which is presently about 60% of the primary nickel market, so things are in balance. Class 1 nickel has also historically been utilized in stainless steel production by necessity, but this proportion has been shrinking due to the emergence of NPI and also the demand for alternate uses of high purity nickel. Specialty alloys, electroplating, and battery precursor production all require Class 1 nickel as the feedstock. Forecasts for nickel demand growth in battery production vary widely as the preferred battery chemistry continues to evolve and the uptake of electrical vehicles by consumers begins to shift. But it's an undeniable fact that there is going to be an increase in the production of nickel for the rapidly growing battery market. Where is this future supply of nickel going to come from? There have been few recent new sulfide mines discovered and developed, and the majority of them have been required to replace depleted sulfide ore bodies. As an example, the Kabanga deposit in Tanzania is world-class in terms of size and grade, but remains undeveloped due to major infrastructure challenges. In the late 1990s, it was claimed that new high-pressure acid leaching technology would completely disrupt the primary nickel industry. Looking now, 20 years later, there are about 5 operating HPAL plants, and they all sit on the upper half of the industry cost curve. There is some recent interest in building HPAL facilities in Indonesia, but the challenges associated with tailings management in a high rainfall climate and high processing costs remain unresolved. A third potential source of future nickel production to serve the battery market is the conversion of NPI to matte. PT Valles has been producing nickel matte from laterite ore in Indonesia for over 50 years, using a slightly modified version of the standard RKEF process. Sulfur is added to the rotary kiln, yielding nickel matte instead of ferronickel. Standard converting furnaces are used for upgrading the matte to a refinery feedstock. That matte is refined in Japan to produce electrolytic nickel and nickel sulfate. It would be a very minor adjustment to adapt this process to an RKEF producing nickel pig iron. Tsingshan has already started to pursue the production of nickel matte in Indonesia. After a successful trial run in one of their NPI plants, they expect to have 2 RKEF lines converted to matte production within the next 6 months. They've also recently signed 2 contracts with refineries in China to supply 100,000 tons of nickel matte, equivalent to 75,000 tons of contained nickel. Therefore, it can only be expected that Tsingshan will continue to be agile in shifting their production profile based on market economics, as they have done in the past with NPI and other ferroalloys. Based on their vertical integration in stainless steel production, it's also very likely that Tsingshan will progressively move downstream into battery precursor production, with refineries dedicated to the production of nickel sulfate. Therefore, we should fully expect Tsingshan to become an important nickel producer within the EV battery supply chain as this market grows. Thank you very much for your interest and attention.
Good day to everyone, wherever you are in the world. Hope you're all doing well. So my name is Lourdes. Currently, I work for BHP Resource Center of Excellence. I was asked by a good friend, Jeff, who is my ex-colleague from SNC-Lavalin, to share with you some of my knowledge and experience in high-pressure acid leaching and the intermediate products that can be produced from HPAL. So as you all know, laterite or nickel oxide is one of the sources, major sources of nickel in the world. And oxide, majority of the low-grade oxide cannot be smelted, and the processing route to extract the value is mostly through leaching. And high-pressure leaching is, or HPAL, is one of the more popular routes. A lot of operations have tried it, and there are some varied levels of successes and failure. So let me go through with you some of the few slides that I have prepared. Just to set the context and the setting for HPAL. You're all familiar with the nickel laterite profile. So the lower grade nickel laterites are more amenable to leaching, primarily because the magnesium content is much more lower. And magnesium is the primary acid consumer that dictates the economics of leaching. So that's why when you select leaching as the extractive route for nickel laterites, the grade has to justify the economics. And particularly with HPAL, where it requires more extensive capital intensity, a head grade of greater than 1% nickel is ideal. So why HPAL? I mean, there's been a lot of failure, but people are still seeking to try see the viability of HPAL for their ore deposit. That's because HPAL, or high pressure acid leaching, is very selective towards nickel and cobalt, leaving majority of the iron in the residue. So as you know, nickel laterite is composed, majority of the mineralogy in nickel laterite is around 30 to 50% iron. So if majority of that iron is extracted into the pregnant liquor solution, it will be an impurity, and removing it downstream is very costly. And along the way, there's a lot of losses of nickel and cobalt as you remove the iron. So that's why, as contentious as it is, a lot of operators are chasing HPAL because of its selectivity. So at higher temperature and pressure, what makes it selective is the hydrolysis of the iron. So the hydrolysis of the iron brought about two important aspects of the leaching process. Firstly, the iron that's extracted from the very beginning of the leaching process at higher temperature, it will combine with water, and then the iron will reprecipitate in the residue as a stable hematite residue. So meaning to say it will not redissolve back into the solution. So that makes it selective in terms of leaching. And secondly, in that process, as the iron reprecipitate back from the liquid to solid, it gives up sulfuric acid as a byproduct. So that makes the whole process the acid consumption of the whole process is reduced, and the net consumption is much lower compared to atmospheric leaching, where the leaching of iron will not give off sulfuric acid. And of course, at higher pressure and temperature, the kinetics of the leaching is faster and it's higher. That's why nickel and cobalt recovery are in excesses of 90%. And from that pregnant liquor solution, which contains the nickel and cobalt, nickel and cobalt can be recovered downstream as an intermediate product, either as a mixed sulfide product or mixed hydroxide product. As a general overview, we have discussed earlier that HPAL has been marred with a lot of technical difficulties, in as much as we have seen in some of the operating plants that's been installed around the world. And it's very true. As you can see in this graph of ramp up, for some of the majority of the nickel HPAL plants, the ramp up of the early HPAL plants are, and even the recent plants, they're very slow. And this graph clearly shows that the ones that are slower, they are the ones that really destroyed a lot of their project value early on in the life cycle. But as you can see, it's like a parting of the Red Sea, where you can see in the left is a very steep ramp up that's only achieved by very few operations. And these operations are not it's not a coincidental that they're owned by the same company. So both Coral Bay Line 1 and Line 2. I used to work for Coral Bay Line 1. We are one of the pioneer crews in this operation. So Line 1, so Sumitomo started with Line 1 first. And then once we get all the technical de-risking, as well as the skills and knowledge, then the company expanded to Line 2. So with Line 2, it was a very fast ramp up because of the acquired skills and knowledge. And it's a strategic capability that really made it. And Line 2 ramp up in just 6 months, and they're able to achieve 100% capacity. Not 100% capacity of nickel, annualized nickel, but the 100% operating capacity. So when they have proven Line 2 as well, then Sumitomo embarked on a more in a bigger scale project to prove the scalability of HPAL. And Taganito, as you can see here, also has the same ramp-up profile, and it's able to achieve its ramp-up in less than 4 years. So Taganito is about 3 times the size of the first HPAL in line 1, but still it's able to demonstrate the same level of successes as what Coral Bay line 1 and line 2 had been. Another interesting curve as well is Ramo Nickel. So Ramo Nickel, after 5 years into the ramp up, they finally able to sustain their design capacity in excess of 100% capacity. So this is a typical flow sheet of an HPAL process. So first, the ore is prepared, basically rejecting majority of the barren ore. So what we're rejecting here is magnesium, which I said earlier consumes a lot of acid, and then prepare the ore into a slurry form and then fed into high pressure acid leaching, where we add acid and high pressure steam to keep the pressure and leach the ore. Then the nickel and cobalt is leached into the solution. But in HPAL, one of the control parameters there is free acid in order to keep your nickel and cobalt in solution. So that free acid, after it's being flashed into an atmospheric condition, it's neutralized using a limestone. And then whatever is the nickel and cobalt values that's entrained within the slurry is washed with a wash water in the counter current decantation. And the pregnant liquor solution then undergoes impurity removal, where majority of the impurities like aluminum and iron are removed with the addition of lime. So it's a pH control impurity removal. So basically the virtually impurity-free pregnant liquor solution is sent into an intermediate product recovery, where nickel and cobalt is dropped out of the solution and precipitated into a solid form by the addition of hydrogen sulfide gas. So you will produce your mixed sulfide product, or you can add magnesium slurry to produce mixed hydroxide product. So these intermediate products, these are the ones that are sent to a downstream refinery to either refine into a class 1 metal or straight into nickel sulfate crystals. So the residue and the tailings from from the high pressure acid leaching is in a slurry form. So, and it still contain a lot of dissolved heavy metals. So the typical route for that is to treat the heavy metals and drop it out from the solution at a very high pH, so that the concentration of the heavy metals met at least in a minimum standard, the World Bank standard. And the slurry is then disposed either in open pit, because majority of the laterite, they have a lot of open pit that is already barren of ore, and that's where the slurry can be contained. And the excess supernatant can either be discharged to the sea, provided that you meet the marine disposal limits, or as like what Coral Bay did, they softened the water and then recycled it back to the process plant. So what are the differences between MSP and MHP products? I will talk about that one in the next slide. But as you can see here, there are a number of operators choosing to produce their intermediate products through mixed sulfide precipitate. So Moa Bay had started it, and then Maran, Coral Bay Nickel in the Philippines, as well as Taganito and Ambarubi, they all produce mixed sulfide product. While Ramo, Gordes, and Ravensthorpe nickel in Australia, they chose the MHP route. So MSP is much more cleaner. It is much more selective to a number of impurities compared to MHP. And of course, MSP fetch a better premium because of it's a cleaner intermediate. So in terms of direct comparison, a mixed sulfide processing typically requires higher capital. It's because the process in itself is very corrosive and it's toxic. So it needs to have a scrubbing process and also H2S destruction, and the materials of construction for the area are mostly exotic, whereas mixed hydroxide is typically less aggressive, and the materials of construction can just be constructed out of carbon steel and rubber lining. While in contrast, the operating cost for mixed sulfide is low, and mixed hydroxide is relatively high because of the high cost of MgO. So as what I have mentioned, for mixed sulfide, the precipitating agent is either H2S gas or NaSH. For MHP, it's MgO slurry. So this is a typical mixed sulfide product. It's dark gray to black color, while mixed hydroxide is it's a green precipitate. And like what I mentioned earlier, mixed sulfide is very selective to a number of impurities, producing a much cleaner intermediate compared to mixed hydroxide, particularly with iron as one of the major impurities and hard to remove downstream. As a side-by-side comparison with typical analysis, we can see here that in mixed sulfide product, it contains a lot more nickel per ton of the precipitate compared to a mixed hydroxide product. And you can see here in the iron, mixed sulfide is much more selective to the precipitation of iron, particularly if the iron is in +3 species. So with mixed hydroxide, it will precipitate very, very easily, but with mixed sulfide, it will still be reduced first to a divalent before it can be precipitated as iron sulfide. Also, if you look at manganese, because this is one of the, I think, the penalty element for downstream processing. So with mixed sulfide, the manganese is of ppm levels, while in mixed hydroxide, it could be up to 6%. Calcium also is very low with mixed sulfide, and silicon. So silicon is one of the controlled impurities as well. So with mixed sulfide, it's down to ppm levels compared to around 0.5% for mixed hydroxide. And also another thing to note is the moisture content of the intermediate product. So with mixed sulfide product, the PSD is much more coarser and it's very easy to filter. So that's why a moisture of around 10 to 15% is typical compared to mixed hydroxide, which tends to absorb more water. And as you can see, the moisture could get up high as around 48 to 55%.
Fantastic. Hello, Johnna again. Lourdes, hello.
Hello,
And
everyone.
hello. And Ron, thanks for being here. Guys, yet again, I think we haven't allowed enough time for this. That was some fantastic sessions from all of you. We started to get a little bit technical there, and I guess we're starting to understand why some of the costs are as they are. For this Q&A, lots of questions sent in. We're going to bounce around and alternate between sulfide, laterite, and HPAL, and NPI, and lots of different topics. So if you're answering, guys, try and be clear about what you're answering about, if we may. So Johnna, I'm going to start with you, if you're okay. So
Yeah, no
thank you very
problem,
much for your presentation. I got big rock, little rock, froth. That's my takeaway. But
there you go.
there you go. But sounds simple, but it's not.
I must say, it feels like there were a lot of years in school to just go big rock, little rock, froth, but that's okay.
It's what I got.
Hey.
But in that, what you showed us was the amount of energy required, the amount of engineering flow sheets need to be very precise. You need to optimize this and to be able to get it right economically. You're big on the economics. So have we reached a stage where we have optimized as much as we're going to optimize?
Oh, no, not at all. I mean, I think there's always opportunities. There's new technology being developed all the time. Specifically, as I think things will change as we go forward too. Like right now, I mean, reality is, and I think maybe we don't want to say this, is a lot of the changes that have come in the industry over the last few years, like let's say the last 50 years, I don't know if they're necessarily innovation or we've just made things bigger. So there's been innovations, of course, and there's been changes, but I think from the mineral processing side, if you were designing a mill in the 1950s or 60s, while things have changed over the years, we still have, things have mostly just gotten bigger, which means that you can get more throughput for less cost. And so, I mean, I think that's kind of reached a point, and maybe things will continue to get a bit bigger, but I think, on top, what we're seeing now is we'll probably see more things coming in on the innovation side where, right now we take all of the ore and we shove it through the mill to get a very small amount of material out. Maybe that will change. People, looked at sorting. People are looking at all sorts of other technologies, some still very theoretical, but that works ongoing. Things like microwaving and naturally breaking rock apart and a whole pile of stuff that is super technical. And right now, sort of the PhD theses and the research is out there. But I think we will start to see some of that come up because I think, to date, while there's been innovation, especially on the automation side of things and things like that, I think a lot of it has really just gotten bigger. And that's why we're talking about some of these larger scale deposits now.
Okay, so we've optimized costs to a degree, but technology may enhance that, and we've maybe got a ways to go in terms of enhancing recovery.
Oh, for sure. I mean, that's absolutely. I mean, right now, if we look at nickel ultramafic specifically, and we look at nickel in general, nickel is one of like I discussed, nickel is in mineral processing, nickel is one of the few minerals where we have nickel present in recoverable form and non-recoverable form. And that exists differently for different deposits, depending on if you're in a massive sulfide deposit where that unrecoverable nickel or nickel you don't want as much is in the pyrrhotite, or in ultramafics where it's more in the serpentine, olivine, and the host rock. And so, I mean, I think there's an opportunity there to look at recovery. I don't know what that's going to look like yet. That needs to come. But I do think that potentially, that's sort of the holy grail of the future, where we look at how do we get all of the nickel out.
Fantastic. Lourdes, thanks for joining us, BP Center of Excellence. You must be able to tell us, why is Indonesia so much better at HPAL than the rest of the world?
Matt, sorry, I didn't get your question. Why is?
Indonesia seems very capable and very good at building HPAL plants.
Okay.
And the economics seem to look a lot better than they do elsewhere. Why is that?
So I'm speaking just based on my experience. I don't represent anybody, but I work for engineering companies for a very long time, and we have a lot of projects in Indonesia. So firstly, the Indonesian nickel laterite grade is relatively higher. So like what I said, anything above 1% generally improves the capital intensity per head grade of the plant that you're about to build. The other key factor is the availability of low power. So there's abundance of low cost coal in Indonesia. Also the government, you should not discount the role of the government here, because they're very supportive in terms of mine development, as opposed to other jurisdictions where there's lots of good laterites, but the geographical and the political situation are really the barriers for development. The other thing too as well is the proximity to acid sources, like big copper smelters are existing within Indonesia. And as you know, one of the biggest components in the OPEX is really the acid and the labor. So, and the labor, typically the labor in Asia are much more agile, very adaptive, and that's what you need really in a successful complex operation like HPAL. You need a workforce that be able to mobilize decision making right from the factory floor, and that's what makes it successful for a number of these complex operations that's existing in Asia. You look at the Chinese; they're very, very agile, very adaptive, as well as the Japanese and the Filipinos, very agile to adapt complex processing that's outside of the status quo or the business as usual.
Thank you. And Ron, welcome. Thank you very much for your presentation. Tsingshan put out a tweet a couple of months ago, got the market talking, and they were talking about MAT. I mean, how do you feel the market has reacted to that? Because investors were slightly confused as to why they would do that.
Yeah, I think there was a bit of maybe an overreaction at the time, but I do think longer term it's going to be a reality as a very natural extension of their foray into the nickel, being a huge nickel producer over the last, barely been over 10 years since they joined the market and joined the industry. So it's and Lourdes, as you said, both in China and Indonesia, they've been very agile and shown that they're not tied to any particular view of what their business should be. Their business clearly is making money, and they're going to adapt as they need to. They turn on, turn off production as demand indicates. And so I can see that it is just a very natural progression for them to really become take a very serious run at being a matte producer as this shift between the demand for class 1 nickel starts to broaden. That's certainly the way they're going to go.
So there's some big conversations again about class 1 versus class 2 versus intermediates. We're seeing lots of different feeds being discussed. How is the existing technology going to deal with that? And if I may throw in another question at the same time, which is the last smelter built was in Miami, 1970s-ish. Is there going to be a more joined up and more cohesive approach to actually dealing with the demands of the nickel market going forward with regards to infrastructure?
I think certainly in Indonesia, there's a pretty cohesive approach being taken from what we can see. And for example, I think the industrial site that's been created in Morowali has really become a center, not just for Tsingshan, although they were the kind of the key initiator and have become a real anchor to create that the scale that's there. But it's now being built on to start to centralize. I could see power generation. Other producers are going to be able to come into that site and not necessarily power plant, because they're starting to create this sort of scale now where they can have some provide some infrastructure. So I think there's going to be certainly in Indonesia something that's a bit more cohesive. Not necessarily outside of that. I think the nickel market, the nickel producers historically, I think have been quite different from copper. They've preferred to act independently. They've been much less prone to share information. Whereas I think copper on the, say, for example, on the copper smelting side, copper processing, that they've recognized that they've got a lot in common, a lot of common challenges and issues, and they can learn from each other. Nickel has not been that way, maybe because there's fewer players, smaller market, very individualized ore deposits. IP is considered to be somewhat, maybe higher valued in the nickel processing industry. So it's developed differently, and I think it's probably going to stay a little bit that way as well.
Lourdes, would you agree?
Maybe in the sulfide world, but in nickel laterite, with all due fairness, there's a large amount of generous information that have been shared across the nickel laterite community. So come to think of it, if it's not shared, the technology is highly imitable right now. It's because of the technology that has been shared. So resources are so mobile, you can just hire one people from another, and yet you see this failure. So somewhere in the middle, there's really a difference between what makes a successful HPAL, because in terms of if we would like to blame it to the lessons learned and not enough information that has been shared, it's different in nickel laterite. I mean, when I look at the information that has been shared with Coral Bay, if I don't know Coral Bay, I could easily design a similar plant in the same specification as what Coral Bay is right now. But still other people, other operations have different outcomes. It's because, the culture, the history of the organization, and then the underlying philosophy are really different. And that's what sets the fundamental difference in terms of my experience in seeing this number of HPAL operations, not just from a spectator point of view, but really being involved in the factory floor point of view.
Brilliant. And actually, I've got a question for you, Johnna. This one's been sent in, quite a good one. Could you please explain payable nickel and, while you're at it, I guess, treatment charges and refining charges?
Sure. This answer specifically applies to when we talk about sulfides. So we're not talking as much about the laterites, but in a sulfide plant, as I discussed, there's several different stages. So we start with the ore in the mine, and then it goes into the mill where you make a concentrate. And that concentrate is an intermediate product. And then generally nickel, as Ron sort of alluded to, nickel is still very vertically integrated. So many of the smelters today are fed almost exclusively by their own mines. They all take a bit of custom feed in general, but generally most of the concentrate that goes to that smelter comes from the mines in the area or the mines that they own. So when you've got a mine and a mill alone, you need to sell your concentrate to somebody. And that concentrate needs to then get processed to go further downstream and produce whatever product it's going to become. That could be pure metal, that could be stainless steel, however that works. So when we talk about payability, we talk about what the downstream processing is willing to pay the concentrate producer for the nickel. And, and many of those, especially in the nickel space, are confidential. So you won't find a lot of information about that. You'll see it in studies, but it is difficult to find that information. And that's sort of a difference between the copper industry. You can find copper terms, but it varies because all the concentrates vary. So it varies depending on what you have in your concentrate, the grade of your concentrate, the byproduct credits in your concentrate, what process you're selling it into, that sort of thing.
Lourdes, is it the same with HPAL?
Yes, it's the same. Depending on the product. So say, for example, MSP, as I believe it's a higher premium compared to MHP, specifically because of those impurities that's associated with the product.
Okay, and obviously we've got a few questions here. Obviously, someone's trying to put a spreadsheet together. What are the latest ranges for dollars per ton of capacity for processing of nickel, of the intermediate, and then into the final product? Ron, do you want to pick that up? Losing him.
Yeah, I don't have any numbers right at hand, but certainly some could follow up with post this this session.
Any thoughts, Johnna?
Sorry. Yeah, I mean, I think I'll just talk to the mill specifically, because that's sort of where my understanding is better. You know, I think you're seeing a range, and it really depends on the size of the mill. You know, I think one thing I talked about earlier is the scale as things get bigger. If you have a small, let's say, SAG mill that grinds up the rocks, you know, that if that's a small mill and is processing, let's say, 2,000 tons per day, you still need one operator, one helper, one laborer. Whereas if you have a 40-foot SAG mill that's processing, say, 50,000 tons per day, you still have that one operator, one laborer, one helper. So, you know, in terms of scale, the milling cost is really reflected in that scale, and can range from sort of in the milling side of things, you know, $5 per ton up to $20, $25 per ton, depending on the size of the mill. There's no one answer fits all, but you do have to look at it when you look at these things. If you've got somebody who's building a, you know, 2,000 ton per day mill, and they say they're going to mill for $5 a pound, that might be a bit questionable. Whereas, you know, a bigger mill, and that's where sort of the comparisons to porphyry copper can come in.
Right, okay, fantastic. And actually one more for you again. I'm trying to do as many of the questions that have been sent in as possible rather than questions I may have for you. So this one's from the audience. Johnna, could you speak to the risk of identifying nickel recoveries in ultramafic ores, and what's the typical value range?
Yeah, and they can range. I mean, the ultramafics, it depends on how much nickel's in the silicate, and so that's, you know, that's key. If investors are going to look at anything, I think you need to look at, are the companies you're looking at talking about variability? Are they talking about assessing the variability of their deposits? Are they talking about nickel and silicates? Are they talking about, you know, recovery, non-recoverable minerals? If they're not, that may raise some questions that maybe they don't know yet. And if they are, then it can range, you know, recoveries can range in these deposits from lows in the 30s to 40s, and, you know, some of them are high as 70s for some of the higher grade ultramafics. But, you know, it's not necessarily about the absolute number, because it's about how much data supports that number, in my opinion. Because if you've got a lot of data that supports a 40-45% recovery, and that the economics work on that, then, you know, that could be a very acceptable project. Whereas if there's not a lot of data and it's 70% recovery, perhaps there's some questions you might want to raise there. So okay, I think it's more just looking at that. I really believe it's around looking at the data to support the number, not the absolute number, because the absolute number, when multiplied by the assumptions around throughput and a cost and nickel market, you know, that's math, right? So that's just the math. So you have to kind of look into how much support is there for that math.
Okay, brilliant. Thank you for that. Lourdes, I might finish with you, if I may. Investors, when looking around the world where the nickel supply is coming from, they look to Asia. It's a little bit opaque in terms of how business gets done there. ESG is a big driver now, and obviously you work with and advise, you know, big companies, and they may be approaching this the right way. But are you seeing enough change by Indonesian government, the Philippine government, by China in terms of the way that they produce nickel in whatever form they produce nickel?
Yeah, okay, let me start with the Philippines first, Matthew. So Philippines, it depends on who are the investor, because the one that I worked with before is Sumitomo Metal Mining Company, and their philosophy is relevant 300 years ago, relevant at present, and will still be relevant in the future, and that is they want to make the community better before they arrive to mine and after they left and finished the mine. And that's exactly what they have shown in the Philippines. The tailings dam that we have operated, as an example, you know, I encourage you to search it on the internet. It's very popular, and even if you have the chance to visit it in the Philippines, the moment that we operated the tailings dam is the moment we think about how we decommission it and rehabilitate it. And during that process, indigenous farmers were consulted on how to rehabilitate the tailings dam into a usable land, because before the mining was there, they used to grow agricultural products out of laterite, which is very difficult and not a fertile land. So when it was decommissioned, they transformed it into an agricultural land toiled by indigenous communities. So now it's a source of livelihood for the community. And Coral Bay just pay for them for fertilizer, equipment for a very low OPEX. But the community is really gaining a lot of value out of it. And another example of ESG as well is the supernatant decant coming from the TSF, because it's a positive water balance. So we have to discharge it, the excess, we have to discharge it to the sea. So with the Japanese specification, the minimum standard in any project is to satisfy the World Bank standard. But for the Japanese, it's not good enough. So that's why at Coral Bay, we really have to operate with the Japanese standard. So the manganese, I will tell you, the Philippine regulation, 0 ppm for manganese. No limits for manganese. For World Bank, it's 10 ppm. For the Japanese, 2 to 4 ppm, and that's what we are sticking for. I do remember in one occasion that we had to stop the plant because we could not achieve the manganese level that we want undiluted. So to me, that is a very, very concrete example of an integrity, that you're living by what is your philosophy and what you want to achieve for the betterment of the community, not just for your business. So it's truly for the interest of the community that they have operated with. I'm not sure about Indonesia, but now with the increasing call coming from the external stakeholders, the Indonesian government is starting to realize that deep sea tailings disposal is really not acceptable. So now you're starting to see the legend HPAL. They're now heading towards filtered tailings because there's no real estate for a tailings dam. So that's a good start and a good push.
Okay, this has been the start of a very good conversation, which I hope we can continue with you at a later date. Thank you very much, Johnna. It's really enlightening. And Ron, thanks for staying with us. And Lourdes, hopefully see you soon. Thank you very much, guys.
Thank you very much. Have a great day.
In this session, we'll be talking about the refining processing for the end uses of nickel. Brian Oliver will be presenting the different flow sheets that are required to go from primary processing, which produces an intermediate, to the final metal products. In nickel, this is quite complicated because there's several different flow sheets and many different products associated with this. In addition, Mark Selby will be reviewing the battery metal feeds for precursors.
Hello everyone, my name is Brian Oliver. I'm a product manager for Valles Base Metals Marketing based out of Toronto. I hope everyone's well during this time. I'm speaking to you from the scenic town of Port Hope, about an hour away from Toronto, about nickel refining processes and products. So some of my colleagues would have already spoken to you about the processes and some of the considerations that go into mining nickel ore bodies, whether they're sulfides or laterites, as well as the basic processing of them, whether that's mineral processing, grinding, milling, concentrating, hydrometallurgy, so leaching, or pyrometallurgical smelting operations. Our colleagues covered how these types of intermediate products are produced. And really what this presentation is meant to cover is how these intermediate products are then transformed into final nickel products that are used across the world in a variety of industries. So looking across the global landscape of all of the primary nickel producers, what we see is there's an awful lot of variety and technical complexity in the world of nickel refining. In some cases, there's perhaps more variety than you would see in the refining processes for other metals, such as copper. And we're going to get into that a little bit, but looking at it at a high level, most of the nickel metal is refined via 4 main processes. So on the left, you have what's called carbonyl refining, and it mostly treats nickel mattes to produce nickel metal. You also have what's called electrolytic refining, and that can treat a variety of feeds, whether it's nickel matte, which would be traditional, or nickel sulfide concentrates. And electricity is used to electroplate metals. Another major processing route involves leaching nickel intermediates in an ammonia-containing solution, and then adding hydrogen gas to make nickel metal. And finally, you have more traditional pyrometallurgical refining processes. So I'm going to just spend a minute or two on each one, just explaining at a high level how these processes work and what the products are that derive from them. So carbonyl refining, what this refers to is a chemical reaction that takes place between nickel and carbon monoxide at certain pressures and temperatures to produce a gas called nickel carbonyl. And so this slide is just showing where this process was first commercialized in Clydach in Wales in 1902. It's now Valles, Europe, as well as a photo of some of the final nickel pellet that's produced there. And so the way this works is you have pellets starting from a very small size, and they're recycled around and around through a column. And each time they pass through this column, they're contacted with more of this nickel-containing nickel carbonyl gas, and a fresh layer of nickel is deposited on the pellet. And so after about several weeks, you have a nickel pellet of usable commercial size, give or take a centimeter in diameter, and it's screened out and ultimately packaged as a product. So this process works so well because nickel is the only metal really that reacts with carbon monoxide gas this way. So it's a very conceptually simple refining process. It's the oldest commercial refining process for pure nickel, but there is some complexity that goes into it. So there are only 3 practitioners of this method. There's Valles in Europe and in Canada. There's Nornickel in Russia, and then there's Jinshuan in China. So while it's a conceptually simple method, there's a lot of complexity introduced by the toxicity of the nickel carbonyl gas, and this toxicity imposes very stringent engineering requirements on these operations. So the main product of carbonyl refining processes, nickel pellets and powders. So on the left you see nickel pellets produced at Valles Sudbury operations. Very pure material. It's used primarily for melting applications, so think alloy steels, super alloys, and electroplating. And what that means is anything you see out in the world that is chrome plated has a layer of nickel underneath it, and this is one of the forms of nickel used for electroplating. We also roll pellets into various products. They're a little bit easier to handle in some applications. And this process can also be used to produce very fine nickel powders that can then be used in various electronics and chemical applications. So that's the first major refining process. The second major process is called electrolytic refining. And this dates back in principle to the late 1800s, first commercialized in Norway and also in Ontario by the companies that are now Glencore and Valles. And the way this works, if you look at the photo here, you see a diagram, and it's a bath full of nickel-containing salt solution. You have an anode, which is basically a sheet of impure nickel metal, like a nickel intermediate that's been cast into a slab of material. And then on the right-hand side, you have a sheet of pure nickel. And as you pass an electrical current through the anode and the cathode and the plating bath, nickel dissolves from the anode and plates at the cathode. And after 5 or 7 days, you end up with an acceptably thick sheet of very pure nickel metal. So this is just a little bit more context as to what these electrodes look like. So the photo on the top right is actually a photo of the smelter that we operated in Manitoba from the early 1960s until a few years ago. And what it's showing is pouring molten nickel matte that's about 75% pure into a mold. And after several days, that molten nickel matte has then cooled and solidified into a nickel anode, which you can actually see in the bottom photo on the right. And so that's what goes into a plating bath as an anode, dissolves slowly, and is used to plate a nickel cathode. So these have been traditionally fairly labor-intensive operations. However, in recent decades, many refineries have almost fully automated the work that goes into producing nickel this way and have become very efficient. So this is just a view of a modern tank house. It's our new tank house in Newfoundland. And this is half of the nickel tank house shown in the bottom left. And each of these sort of rectangular tanks you see there has about 200 electrodes in it, so anodes and cathodes. And so you may imagine that a big part of refining nickel this way has to do with managing all of those electrodes and the electricity flowing through them. One other point to mention about this form of refining is that all of these refineries producing electrolytic nickel have very customized impurity removal circuits integrated into them. So all of these refineries have been designed and constructed and subsequently modified perhaps to accommodate the chemistry of the feedstocks being fed into them. And that's something that is worth considering regarding the complexity of nickel refining in general. All the refineries are a little bit customized, and in some cases a lot. Finishing up electrolytic nickel. So the majority of electrolytically refined nickel is produced as a slab you see here, give or take a square meter in size, and give or take 10 to 15 millimeters thick. Most of the time, almost all of the time, that material is then sheared into smaller square pieces. So whether it's 1 inch square, as you see in the bottom right photo, 2 inches square or 4 inches square, those are the most common sizes. Simply for handleability reasons, it can be a little bit challenging for customers to handle such a large, maybe 80 kilogram sheet of nickel. One other point is Valles, which was then Inco in the 70s, created a new shape called nickel rounds. There's a photo in the top right of this slide. They're button-shaped pieces that are much safer and easier to handle than cut cathode is, or full-size cathode, as you would see here. So that's really the summary of electrolytic nickel refining. And between carbonyl, electrolytic nickel, those were the two maybe most historical processes or classes of processes used to make pure nickel. However, when we got into the middle of the 20th century, Sherritt Gordon, now called Sherritt, developed a new way to refine nickel. And the way this works is, and you can see a very simplified flow sheet on the right. It's not a real plant. It's just an illustration of how a plant like this is laid out or can work. You can take a variety of sulfide feeds. So originally this process was developed to treat concentrates from northern Manitoba. But also can treat matte, can also treat precipitated intermediates like MSP, if you've heard of that. So this material, the nickel and other metals, are leached in acidic ammoniacal solutions. There are then a series of impurity removal steps that are again customized to the feedstock, customized to the size and other processes in the refinery. Can be somewhat complex chemically, but ultimately exist to remove copper, iron, and a variety of other impurities you may find in the feedstocks. After that, typically there's a cobalt separation that can be done by chemical precipitation. It can be done by a technology called solvent extraction. And so there are a lot of different configurations of these types of processes all over the world. By number of refineries, I believe this would be the most common process in use. Whether it's in Madagascar, Canada, Australia, Finland, it's been successfully commercialized quite widely. And after you generate a pure nickel solution and you generate a pure cobalt solution, then there are a series of vessels into which hydrogen gas is injected, and the hydrogen gas reacts with the nickel in solution to produce a nickel powder. And this isn't a very fine nickel powder like we talked about before. This is several hundred microns in size versus, say, a fine nickel powder that would be under 10 microns in size. And most of the time, these powders are then compacted into a mold and pressed and or sintered into what's called a briquette. It's just typically a small almond-shaped piece of nickel. They do vary in purity depending on the refining process used to produce them. This is a photo that Embatavi shared for us showing briquettes from their facility in Madagascar being packaged for production. Getting into the refining processes used to create less pure forms of nickel, we can talk about utility nickel production. One's very common, now less so. Utility nickel describes a range of steelmaking nickel products that vary in purity from, say, 90 to roughly 98%. The simplest processes involve reducing nickel oxide feed material in a molten state and then flashing that material in water to produce a utility nickel shot. And you can see photos of that happening at a Valles facility in China on this slide, as well as a photo of nickel shot. There are other processes. We operate one in Japan at our Matsuzaka refinery to produce a different type of utility nickel that we call TonyMet. We've branded it as TonyMet, and we produce that in granules or briquettes. This has become a less common refining route in recent years due to the increased prevalence of nickel pig iron production and nickel pig iron usage in the stainless steel industry. So getting into that a little bit, I think my colleagues have probably elaborated on it more than I'm even capable of doing, but I'll just touch on it quickly. So ferronickel basically is a class of nickel products that contains iron still in significant quantities. So traditionally about 25 to 35% nickel. That's what people call ferronickel today. Lower grade ferronickel is what is now called nickel pig iron, and so that's typically below 15% nickel. So there are a number of variants of these processes. I think others will have touched on. I mean, ours in Brazil at our Onça Puma facility is quite simple. The ore comes out of the ground. It's a laterite ore. It's crushed. It has to be dried, and calcining means driving the contained moisture out of the ore. So there are a couple of different kilning stages. It's basically refined in electric furnace and ladles, and then it's shotted to produce ferronickel, which you see in the photo here. Finally, nickel sulfate production really can be produced in one of three main ways. It can be crystallized from process solutions in refineries that are already producing nickel metal. So there are examples of this around the world. You can dissolve an intermediate like MHP, like MSP, with the intention of only producing nickel sulfate and not producing metallic products. That's happening maybe more frequently now than it has in the past. And finally, you can dissolve nickel metal powders or briquettes, and even other forms for that matter, and then crystallize the material as nickel sulfate. So in any event, a producer wishing to do this will have to customize their process based on the feed that they intend to purchase or intend to use. There's no really simple way of, hey, making a nickel sulfate plant that can take any and all feeds in an economical way that I'm aware of. Of course, there are lots of people looking at this all the time. So that was a very high level view of sort of the main nickel refining processes, as well as the products that come out of them. And I'm just going to take a quick moment and talk a little bit about where all these products go. So when you look at demand for nickel, in a given year, about 70% of the nickel produced is consumed to make stainless steel. 2020 was a little bit higher. Some years it's a little bit lower, but that's about the number. And then if you look at uses outside of stainless steel, so electroplating, production of specialty alloys used in automotive, aerospace, industrial applications, that's about 25% of the market. And then finally, today, batteries, well, projected to grow at very exciting rates in the next 1 to 2 decades. Today, it's still a small percentage of the market, about 5%, give or take. And by the way, that's not just electric vehicles. There are other forms of batteries, nickel metal hydride, even NiCad, that still have some industrial applications, even though they're not talked about very widely anymore. Finally, this is a bit of a complex diagram, but it's my attempt to perhaps distill some of the flows of nickel material from their ore bodies through the various processes to refine them into finished products, and then finally how and why they're sent to end users in different industries. I want to just preface this a little bit by saying this is not exhaustive. The world of nickel processing has a lot of complexity. This is meant to be a very simplified view of the entire value chain from ore to end-use markets. And so, I mean, through the course of these sessions, you will have seen a lot about how laterite ores are processed via smelting or HPAL processes, how they can be turned into nickel matte like we've been doing in Indonesia since the 70s, versus HPAL processes that typically produce intermediates. Sulfide ores essentially are always ground and concentrated, with very minor exceptions, to make a concentrate that's about 10 to 20% nickel. From there, they can be smelted or treated electrochemically or hydrometallurgically, in fact, via the refining processes we talked about. And finally, kind of get a view of the various nickel products we talked about. And at the top of the slide, you see sort of the lower purity nickel products, nickel pig iron, moving down through utility nickel, briquettes, sulfates, and then you get into the higher purity electrolytics and carbonyl nickel products. What we call first use markets: stainless steel, still about 70%, electroplating and superalloys, other nickel alloys, all account for 7 to 8% of the market each. Everything else, including the batteries, 5 to 7%. And then from there, these primary nickel products, alloys and others, move to what we call end-use markets, which are primarily driven by transportation sectors, construction sectors, and industrial sectors. So a very brief overview of nickel refining processes and products. I'd like to thank you all for listening today, and I'd be very happy if you have any questions to try to answer them.
Well, I hope everyone has been enjoying the sessions over the last 2 days. As part of the refining session, we thought it would be good to spend a few extra slides just commenting on some of the specific changes, that are occurring and we think will occur in the battery feed, the EV supply chain. As obviously that's going to be a critical part of the market going forward. The Tesla Battery Day presentation did a great job explaining, their philosophy around how they see batteries coming together, and how they see cathode materials coming together. And if you have not seen it, I would encourage you to watch it. One of the key thrusts, again, they took each part of the battery and described how they're going to make improvements to it. And so one of the key components was around the cathode materials themselves. And the thing that they mentioned and really highlighted was just what a convoluted, inefficient approach nickel sulfate is as a way to get nickel, a nickel atom basically, into a battery. And again, they had very colorful comments around that, which I won't repeat here. But again, they made it very clear that the current system does not work from providing the lowest cost nickel feed into the overall supply chain. Nickel sulfate's fundamental issue is only 22% nickel in its pure form. The rest of what's there is water and sulfate. So you end up shipping something, that actually contains very little nickel. Most of the feeds that you actually use to produce that nickel sulfate actually start out with higher nickel contents. They have other impurities, which the refining process gets rid of, but you're just substituting water and sulfate for other impurities. So again, the process is not helpful on that front. And then thirdly, the final step in the sulfate process is to take it out of solution, crystallize it so you can put it in a bag and then ship it somewhere. And then the very first thing the customer does when they receive that product is then redissolve it again. So you've got energy required to precipitate it. Then you have to use acid, more energy to get it back into solution again. So where they were very much focused on is let's use nickel once, get it into a battery product, and you can see in the bottom right corner with less stuff happening to get to that final cathode precursor material. The other big point that they really emphasized in terms of creating local integrated supply chains, on the map of the U.S. and Canada, they made it clear that they want to source nickel and lithium closer to home. Again, in an auto supply chain, you have component manufacturers located in close proximity to the car production plant. So again, you're trying to minimize the overall supply chain of that material. And you can see here, where they're focused on and measuring what that, basically weight times distance that the various materials need to travel to be able to provide that product into their batteries. So again, this is something that's very top of mind for Tesla, and I know from other discussions with various participants in the supply chain. What I think you're going to see more and more often emerge as we get new sources of supply, and that new source of supply isn't stuck with some legacy processing facilities that they need to utilize, is you'll see integrated precursor production co-located with production sites. So you've already seen BASF basically build a battery plant where they're taking the nickel out of solution at the Norilsk refinery and precipitating it out into a product they can use, as opposed to letting Norilsk do the additional work and then just shipping it to a BASF factory located elsewhere. EcoPro announced it was working with Blackstone, again, looking at a place where you could take concentrate feeds from Blackstone's mines in the future in Vietnam and convert them again right through into a precursor material in Vietnam before being shipped off elsewhere. Now, we obviously, those who follow the nickel market saw the Qingshan announcement where they're using the 50-year-old PT Inco process to take saprolite ore and make matte to ship that to precursor producers in China. Again, with the view, it'll be basically dissolved once and end up in a precursor all within one facility. And so, as markets get comfortable with different nickel feeds, you're going to see them continue to move up the feed chain, and you will see increased use of concentrates and other intermediates as a source of feed rather than paying up for refined metal. That creates great opportunities for mining operations that are in the right locations, where they are co-located or not co-located, or in close proximity to auto plants in the United States and Europe. And again, if you're able to produce as a miner, you now really need to focus on producing the best concentrate or intermediate that you can, for that EV supply chain. And again, those companies that are able to do that and able to partner properly, I think will come out a winner. So it'll be very interesting to see, how this evolves, as again, a massive amount of value is going to be unlocked over the next few years.
That was a fantastic session, guys. Refining and processing for end use of nickel. Learned a thing or two from that. We're going to go now straight into recycling. Now, that's a big topic. We've talked about this many times on our weekly nickel show on the Crux Investor Club, and it plays a big part in the industry. So, Mark Mistry, off you go.
So good day. My name is Mark Mistry. I work for the Nickel Institute, and I'm going to talk today about nickel and recycling. There are 4 topics that I would like to cover in the following slides with my presentation. First of all, a few words about the recycling of metals in general before I then go into nickel recycling. I will highlight a few benefits and then talk about the efficiencies that we see in the recycling of nickel and where we see linked to it some potential to improve. So to start off, often enough we say that recycling is actually part of the DNA of metals, such as, for example, nickel. So different than other raw materials, metals can be recycled without a loss of their properties or the quality. And it is important to understand that recycled metal cannot be really distinguished from primary metal. It's the same quality. The other point I would like to highlight is that the recycling of metals is as old as the production of metals. So often enough we hear right now politicians talking about circular economy being a new concept, but in the case of metals, it's something that we are doing already since several thousand years. And the last point I would like to mention here on this slide is that the quality of metals is described in standards, independent whether they are from recycling or from primary production. They have to fulfill a certain protocol or standard. In our case, it would be an ASTM standard that you can find on the website of the London Metal Exchange. If we look into different groups of raw materials, and I've taken here a chart which is showing 3 main groups, namely non-remeltable materials, such as, for example, concrete, fibrous materials, where you would have wood and paper falling underneath, and metals. We can see that there are major differences throughout the recycling stage. So in the case of metals, which you can find here on the bottom of the chart, you can see that from scrap into the conversion into new products after recycling, metals keep their intrinsic properties. We do not change. And that's a major difference to fibrous materials, where we see, for example, that the fibers in wood or in paper are getting smaller and smaller, or in the case of concrete. So we don't experience any downcycling. We don't have a change in properties. The properties remain the same even after several life cycles. And in theory, it is said that metals can be infinitely recycled. So that's important to keep it in mind when looking into other raw materials. And the benefits of metals recycling are apparent. They are covering all elements, all aspects of sustainable development. It's on the one side economically attractive. It helps to save a lot of energy. It reduces the dependencies on imports, on imported raw materials, which is highly critical, especially for resource-poor regions. It prevents landfilling. And last but not least, it also provides jobs to small and medium-sized businesses. Going right now a step further and looking into the nickel value chains and where the recycling of nickel occurs, I've taken here a Sankey diagram where you can see on the left side the raw materials input. So the green area would describe the primary sources. Then these raw materials are converted into intermediate products, which would be the blue area. Then they are converted into the final nickel products. So that would be nickel metal in different forms and nickel sulfate. And then we have actually the orange area, which would be the first use of nickel. And you can see that there's on the top left, the box scrap. So the material which is available for recycling, which is not passing the nickel industry, but going directly into stainless steel production. So the recycling of nickel takes place predominantly in our major first use industry, which is the stainless steel sector. And that is mainly linked to the fact that more than 85% of all nickel is used as an alloying element, predominantly as stainless steel. So it wouldn't make any sense to actually try and get the nickel out of the alloy as such. That would be far too energy intensive. So what you do is actually you recycle the alloy as such. And that's a major difference to other metals like copper, aluminium, carbon steel, lead, where the recycling is actually an integrated part of the smelting and refining activities. But there's one important point, and that is actually batteries. As you might be aware, when we talk about EV batteries, we talk about batteries with a high nickel content. So we can expect that through the increasing use of nickel in, for example, the batteries industry, there's also going to be a growing recycling of these batteries within the nickel industry. So that picture might change in the near future. I've taken here a chart that we developed a while ago for the European Union to explain where the different flows for recycling occur in the value chain of nickel. So you can see at the bottom right, the different input materials. So in Europe, we have a certain amount of nickel coming from the mines, which is entering the value chains. And you can see on the left side of this diagram, a number of flows of nickel and nickel-containing goods, which are made available for recycling, and they occur in various stages of the production, manufacturing, and use phase. So there's on the one side process scrap, for example, occurring in the stainless steel mills. We have fabrication scrap, which might occur when I convert my stainless steel into goods and articles. And then we have at the end of the life, the so-called end-of-life scrap. And all these materials are actually recycled. They are recycled, as I mentioned on my slide before, into stainless steel. It is important to note that we also have losses, and they occur here behind the use phase, so behind these blocks that you can see in the middle of the graph. And these losses to the flow, I'm going to talk about them in a minute. An important aspect is that when talking about recycling and improving recycling, you first need to actually have indicators being in place that allow you to quantify how efficient is an industry in recycling, and to also allow to take the right measures in improving the system. And there are so-called recycling indicators existing, which were agreed upon between industry, academics, and regulators a while ago. And the important point is to note that these indicators are used to provide answers to different questions. And I've taken here two questions, like, for example, how much metal is recycled from products such as cars, computers, batteries at the end of life? And then you would use the so-called end-of-life recycling rate. If you want to know something about the share of recycled metal in the overall metal production, you would use the so-called recycled content. And these indicators allow us to assess systems in more detail, to understand how efficient industries are, to understand how much metal is coming from recycling. In the following chart, you can see a Mendeleev table, which was put together by the International Resource Panel of the United Nations. And in this chart, they investigated roughly 60 different elements or metals to understand how big is the share of metal coming from recycling. And you can see that especially those elements which are colored in red or orange, there we have a very low amount of these metals coming from recycling. That has mainly to do with the fact that these metals are only in use since a couple of years. So there are, for the time being, no streams coming back for recycling. Nickel is amongst a group of base metals where the recycled content is around a third, so 33% of all nickel used is coming from recycling. And that has mainly to do with the long lifetime of nickel-containing products, but also the market growth that we see in nickel production. Looking right now into the so-called end-of-life recycling rate, or to answer the question, how efficient are we in the recycling of nickel? You can see that we are amongst a group, again, of base metals, highlighted here in blue, where you can see that the end-of-life recycling rate is far above 50%. That applies to most of the base metals. Again, you can see here that especially the so-called high-tech metals, so for example, rare earth elements, they have a very low recycling efficiency. Again, it has to do with the fact that these metals are only in the market since a couple of years, and there are, for the time being, no recycling systems in place to recover these metals after they are made available for recycling. We have done some further work together with the Yale University Center for Industrial Ecology to better understand how efficient are we in recycling, where do losses occur, and where can we improve the system. So as you can see, we have roughly 68% of all nickel that is in theory available for recycling really entering again another life cycle as nickel. However, we also have 15% of nickel going into the carbon steel loop, where they are recycled, so they are replacing iron atoms. But we describe it as a non-functional recycling, as the nickel which is recycled in carbon steel doesn't add any of its outstanding properties to the carbon steel. And the second more critical area are losses, for example, into landfills, losses into slags or production residues, where clearly there's a lot of potential to further improve in order to strive towards a circular economy. So as a kind of summary, nickel recycling is beneficial from an environmental, economic, social, and geopolitical point of view. Nickel is recycled at highest recycling efficiencies and therefore a material of choice when it comes to sustainability. We identified potential to improve. So that would be on the one side, the area of landfilling, on the other side, the losses into carbon steel. And we are working together with authorities, with academia, to identify the measures which need to be taken, such as consumer education, regulation, and investments into R&D. My last slide, just to recap, we also have on our website an infographic available that you can download, where you can find further information on what I just described. Thank you.
Nickel is powering the electric vehicle revolution, and demand for battery minerals is growing. Canada Nickel is rapidly advancing its Crawford Nickel Cobalt project to be a leading global provider of these essential metals. Canada Nickel Company.
Hi guys. I think Mark Selby is going to try and join us. If he does, that'll be great. I've got one for Brian, actually. This is an attempt as an investor trying to understand how companies make decisions as to how they set themselves up. And I guess China's such a big player in this that they must determine, how companies proceed. So can you just talk to me about what you think the potential is for increased refined nickel supply outside of China is?
Well, there's certainly potential for it, and we're seeing a little bit of it happening already. There were announcements coming out of Harry Volta in the last 2 or 3 weeks, showing some expansions there. There's still a little bit of capacity that's not fully utilized in the existing refineries, although I think that's expected to change in the coming years. There's certainly real opportunities for new refined capacity for products to feed the electric vehicle supply chain, and that's what a lot of this discussion is about. I think the outlook for new refining capacity for metals, there may be some in the coming years, but that's certainly not where most of the growth is going to come from.
Where is the growth coming from?
Facilities producing products catering to the electric vehicle supply chain. So this is MSP facilities, MHP fed into sulfate production, metals fed into sulfate production. People can dissolve cathode, briquettes, other metals to make nickel sulfate. There are some other processing routes being explored to produce battery precursor materials as well. But in any event, that's where the growth is coming from. And there's a lot of excitement and discussion even outside of China around that.
Okay, appreciate that. Thanks, Brian. Boy, here's one for you. Do you think that a custom refinery in the West could be an easier way to bring processing into North America? And in fact, is there anyone thinking about doing it yet?
I don't know if anyone, Mark might know, Brian might know, there's an attempt up in Timmins to do this with cobalt, right? Kind of get a back end foot in the door in terms of domestic production. So there's a cobalt refinery up there, but I don't know if Mark or Brian or Jeff know of any attempts to do this on the nickel side. Mark can't hear you. Mark.
You can't hear me.
Mark.
Okay. Jeff, any thoughts while Mark's sorting out?
Like if you're like, look, this custom refinery is going to cost a lot of money, right? And you have to have the security of feed over 20, 30 years in order to sort of guarantee that, right? So, the first question you have to ask yourself is if you're going to build, say, a matte refinery or something that's going to feed the downstream, that's going to produce final nickel products to feed into precursors, where is the matte going to come from? Can you secure that matte over the next 30 years? At the scale that you need, right, to justify that. But, no one is working on this. These projects take a very long time to develop, as Brian, I know, has personal experience in. If we started today, you'd be hard pressed to get that into operations 5-7 years from now.
Oh, I think you can hear me now.
He's back.
Yes, it's always the operator. In terms of, this is a key thing is, when you look at, you obviously first cobalt's building, we having a cobalt refinery and expanding it, and that's great to see. in terms of nickel refining capacity, nickel processing capacity, that's the, I think in terms of what gets built in North America, people are talking about doing something, but the reality is Long Harbor was nearly $5 billion before it got working. So when people are talking about pressure oxidative leaching, like it's a no-brainer, I'm going to set up a little one next to my mine site and, I'll be up and going in no time. I don't think that's the case. I think there are atmospheric leaching opportunities that you can scalp stuff out at a much lower CapEx. That might make it work. You still have the residual material that you'd need to find a way to process, but that's one real option. Again, with Dumont, we looked at roasting concentrate, and again, looking for ways to get material into the battery supply, into the stainless steel supply chain. But I think the model that will most likely emerge, it's not here now, is similar to what you're seeing with EcoPro with Blackstone in Vietnam, where EcoPro, who is a precursor maker, is working with Blackstone to basically have a plant where concentrate comes in the front end and precursor comes out the back end. And again, it's not the junior miner who's doing it. It's EcoPro, whose business all day long, every day, is refining different materials to make battery precursor. And those are the right people to have their dollars and their expertise to build that plant, not a junior mining company. So I think that's the model that's going to evolve going forward. Yeah.
So, I mean, I guess it's going to be like horses for courses. There's going to be people who go straight to sulfate, and there'll be others that go to making metal and then battery precursors. There's room for all of the above, is there?
There's room for all of the above, but I mean, as I talked about in my presentation, we're echoing what Elon Musk said. Sulfate's a horrible product. It's a really, it exists because that's what was made historically, but taking feeds that are generally way more than 22% nickel to turn it into a 22% nickel product using a huge amount of energy and water to do so, which then gets redissolved again at the next stage as soon as the customer gets it, is dumb. Is a really dumb way to make nickel. So, there are places where it makes sense. Terra Firma in Scandinavia, their process has nickel in solution, and it's just a question of, okay, in solution, how am I going to precipitate it? And there's no car plants in Finland right now, but for them, going to sulfate made sense. Again, I think longer term you'll see a battery precursor, basically, drill a hole in the side of their refinery, stick a pipe in and just take the refined liquor in solution and use that to start making the battery precursor. Sulfate on its own is just a really, really dumb product.
Yeah, I think we've talked about it on the Weekly Nickel Show with you. Okay, so if battery precursor requirements are, this question, are battery precursor requirements driving refinery direction at the moment? Mark, just stick with you on this one.
Oh yeah, they'll have to. I mean, in terms of new capacity, you've got two key markets going forward: stainless steel and EVs. So you either have to build your process to get nickel into the stainless steel chain at the lowest possible cost, or to get nickel into the EV chain at the lowest possible cost. And the reality is the demands of the EV market for even purer and purer, for them to deliver a pure and purer product to the battery makers is going up exponentially. And so again, let's let the battery precursor industry spend the capital. They've got the expertise, to go from 10 parts per billion to 5 parts per billion to 1 part per billion, with that kind of, impurity levels are what they're looking for.
Okay, and so Brian, one for you here. We've heard how complicated some of these flow sheets can be, and the whole process is, it's ridiculously expensive in places too. So, how do existing plants adapt, or how can they be flexible for all of these new incoming feeds?
The reality is today that many of the existing plants that are operating are already processing a variety of different feeds, but they're sensitive to impurities, and the different feedstocks containing different levels of impurities are as a consequence added in very limited quantities to these smelting and refining flow sheets that have been really tailored to treat an existing ore body, usually owned by the smelter and refiner. So if we look around the world, of course, there are great examples of facilities that have been very highly modified to treat different ore bodies. So Fort Saskatchewan, the Sherritt refinery has changed feedstocks over the years. Harry Volta has changed their feedstocks many times over the years. It's something that can be done. It just costs money.
Always. Mark Mistry, hello. I think you're the bit that people didn't know much about, actually. Recycling. You broke it down, and I think made it, quite easy to understand at the different points at which scrap and recycling affects what's going on in the market. Certainly in terms of probably even pricing. Do you think this is what the recycling, as you've described, has become the new norm, or can we expect to see even more from that space?
So, when we talk about recycling and recycling taking place within the nickel industry, we are automatically talking about the future recycling of EV batteries. That is going to be, a mass of nickel, which is coming back into our industry. The challenge that I see is that there are so many question marks that we still have in front of us. It will take a time until these tonnages are actually made available and are coming back to our installations for recycling. We are talking currently about a lifetime of 8 to 10 years. We know that there are discussions around the million-mile battery. We know from different research projects in China, where we already have a lot of electric vehicles on the streets, that before these batteries are really coming back to recycling, they are experiencing a second life or even a third life. So there are so many question marks around recycling of EV batteries that it is really difficult to predict.
Well, can I talk to you about pricing and perhaps new business models out there about the way that producers of battery metals and materials charge for their products? We've seen in vanadium batteries the talk of renting their material. Do you think this could be applied across the board for other metals and materials going into batteries?
Yes, we see similar movements in the batteries value chain. So joint ventures are signed between car manufacturers, battery manufacturers, and raw materials producers. So it is taking place. And you might be aware that, for example, BMW is working closely together, for example, with Umicore, one of the companies which is already very active in the recycling of lithium-ion batteries. So this might become a model.
Mark Selby, what do you think that will do for companies looking to raise finances? Does that make things a lot easier for you?
In terms of, sorry?
Being able to rent rather than sell what you're producing.
Oh, I think, I think there's a tremendous opportunity there that, again, when you really get into sort of a brand new space, and the fact that, we are getting into closed loop systems for a lot of materials, that, there's no reason over time that kind of a rental arrangement with the right amount of capital to fund that large universe of nickel that's going to be utilized. But I think for some clever financiers, there's an opportunity that's out there for sure. So,
and that could help companies get a different type of multiple, I suspect, if you're talking about annuity streams rather than one-off transactions.
Yeah, for sure. No, I think the recyclability of nickel is a tremendous asset to the commodity, and something that not enough people, pay attention to in terms of, why is stainless steel, continuing to gain share from carbon steel and other materials, is because it's a really highly recyclable material that's got great life cycle costs. And I think, Mark's presentation, really highlighted that. So.
It absolutely did. It's fantastic. Well, gentlemen, as we've experienced today, we've run out of time. We just haven't left enough time for the Q&A bit. Some fantastic questions being sent in by everyone. Your questions will be answered. We will get back to you, Mark. So Boyd and Jeff are kind of working their way through that, and if they don't have the answers, they will get the answers and get back to you. I need to thank Mark. Thank you very much for coming and joining us today. Brian, as well. Boyd and Jeff for putting on the show. MetSoc does a great job here. And Mark, I appreciate your time too, because you're also one of the key sponsors. We need to thank you for that. So Canada Nickel, Centaurus Metals, and also the Metal Group have made this possible. All money going to MetSoc for the work that they do. Appreciate everyone who has made time to join us. I'm sorry we've overrun. If it was down to me, we would overrun for another couple of hours, because the questions being sent in are super. The people have been fantastic. I hope everyone has got something from this and making investing just that little bit easier. Boyd, I'm going to let you have the last word. This was your brainchild.
You got all the thanks out there, except to you. Thank you, and to your team. Thanks. I mean, this really being in your arms on this one was a great experience. Thanks for putting this all together very smoothly. And last, thanks to the audience. If we don't have learned investors out there, it just causes trouble for us technical wonks. So we appreciate them taking time to learn the nuts and bolts of this. I think it's important. And look later on if you're into other things besides nickel. Hopefully Crux and MetSoc and CIM will team up again for the next installment in another metal to come.
Thank you very much. See you soon, guys.